invest. We are Azure Quantum ambassadors, and thank you very much for your time today and for your interest in quantum in joining this session, right? So let's just get started. So how we have planned this session is we are going, we heard this introduction from Ket, and after that, what I'm going to do is I'm going to take you through Microsoft Quantum and what is quantum, why it is quantum, and quantum computing basics, the basic concepts that you would need to know in quantum computing to proceed further, right? And Amit has kindly consented to take us through the Q-Sharp and quantum computing virtual lab, where we will actually see how to program on a quantum computer, right, using this Q-Sharp language. And Devika would further be taking us to an optimization deep dive as to how to utilize quantum optimization solvers available for you today, right? So this is the crux of our session, in this workshop. And thanks very much for joining us here. So let's get started. So this is the overview and the basic quantum computing that you would know to you would need to know to step into quantum, right? So this is just a brief about why is quantum computing such a buzz, right? Why is it said it is touted to impact climate change, optimize our natural resources usage, and evolve our evolve our modes of transportation to an ever-growing population. So why is it and how is it so, right? So to tell you quickly, see, we produce a lot of ammonia for fertilizers, right? That is needed for our growing population to feed them. So when we produce ammonia, we use a process called Haber's process. And in this process, when we actually do this, we almost consume 2 to 3% of global energy, and there is a lot of CO2 emission due to this. But if we can synthesize more complex molecules with the help of quantum computing, we can make this whole process much more efficient and reduce our CO2 emissions. So that is how quantum computing can lead us to actually solve global scale problems today, right? So that's why quantum computing is generating a lot of interest, and we will walk through why it is and how it is so also, right? See, this is you can see, like when I say modeling complex molecules, you can see the x-axis is the number of atoms and calculation time is the y-axis. And if you see classical computers today, which are also very powerful, they would take up to the age of universe to actually, as the complexity of the molecule increases. But if you see quantum computing, it is exponentially more powerful here, right? So, so we can actually, with the scalable quantum computers, we would be able to synthesize more complex molecules. So why is this so? What gives quantum computing this power? What is the concepts behind that gives quantum computing this powers, right? So for that, just a little bit about what is transistors today that sits in computers that are front of us right now, right? So they are like a light switch. They can be either in 1 or in 0, right? But in quantum, so that's why what we do, we have to make a classical computer more powerful, we have to pack more and more transistors into a single machine. So now Xbox comprises of almost 5 billion transistors. So that's the scale that we have gone to today. But in quantum computing, right, we have this superposition, the concept of superposition. The concept of a superposition is, from a bit, we transition to something called qubit. Qubit is a fundamental, many of you might know, but for people who may not be familiar, qubit is the fundamental bit of a quantum computer system, right? There is a powerful concept of superposition. Superposition means it can, it is not only, the qubit is not in a like deterministic state, like either 1 or 0. It can simultaneously represent both. When I say simultaneously represent both, what is it is? It is in some probability of either being in a 1 or a 0, right? Like when you flip a coin up, when it lands, it will either be in head or tail, but when you're flipping, it is rotating, right? It is in some probability of 1 or 0, maybe 50% probability of 0 and 50% probability of 1, which is called equal superposition. but it may also be in right the other it can also be in a 70% probability of 1 and 30% probability of 0. So this is the concept of superposition, where qubit is able to simultaneously represent a state, right? So let's go on. So when you see a representation of a 4-bit number, so in the classical computer today, 4 bits can either represent only one of these numbers at a time, right? It can either be 1 or 8 or whatever it is. It can represent only one number at a time. But what can quantum computing do? With 4 bits, it simultaneously represents all 16 of these numbers. Why is it so? Because it is always, when all the qubits are in superposition, it is in some probability, has some probability of reducing to any of these 16 numbers, right? So at any given time, you don't know, it can simultaneously be in some probabilistic distribution of all of these 16 numbers. So that is the power of quantum computing, right? So for representing our 16 numbers, we need 64 bits, 16 into 4 classical bits. But in a quantum computing, this can be achieved in 4 qubits, right? That is what gives the exponential power of quantum computing. And any algorithm in quantum computing will utilize this superposition concept to make the algorithm exponentially faster, right? To understand this scale, let's just compare a quick comparison. 20 qubits would be equivalent to 16 MB, 30 qubits is 16 GB, and 15 is 16 petabytes, right? And when you go to something like 230 qubits, it is 10 to the power of 80 bytes on a classical computer, and that is the entire set of particles on our universe. So when quantum computers are able to go to that scale, then it is a very, very powerful, a power that our classical computers will not be able to achieve, right? So what is the path to scalable quantum computers? So as you may have all guessed, right, it is not just simple transistors. Quantum computers physically are made up of qubits, and they are extremely prone to error. And if you see quantum computer, you might have seen this picture, right? And this picture is what it is, mainly the refrigerator, which is keeping the fragile qubit in a very, very cold temperature, right? There are different methods by which different companies, like a transistor, it is not very standard today. There are different methods different companies are adopting. Microsoft is the only company that is going topological qubits way, which reduces a lot of errors in the qubits. And there are also other methods like superconducting ions that other companies are exploring as well. But the common theme in all of them is to reduce the error. It has to be maintained in a very cold temperature, like it's almost colder than outer space, right? So, so you can see the path of this, this path to scalable quantum computing is only via the cloud. No company will be able to afford it on their data center. So that's why you can see a lot of interest in companies to, in cloud providers to invest in quantum, because quantum is only scalable via the cloud, right? Let's go to the actual applications of quantum today, right? You might have all heard about this cryptography. So, this quantum cryptography, see, this RSA algorithms that we have today is dependent on a large number, and if you can identify the 2 prime numbers that can be multiplied to get this large number, you can actually break this RSA algorithm. But that is not possible in a classical computer today, but it is easily possible on a quantum computer. So there's a lot of research going on the quantum side, on quantum cryptography, to make cryptography secure when quantum computers are available at scale. So this is a small data we are dealing with. On the other end, we have big data like machine learning, and this would need an extremely powerful quantum computer, right? So which we are not at there today. So the sweet spot that Microsoft also sees is optimization and simulation of physical system. In both of this here, like as I was mentioning previously, there are a certain set of problems and algorithms that suit a quantum machine. Quantum machine is not for all algorithms, right? So certain algorithms that have exponential speed up and can be reduced finally to one answer. So if we parallelly run, we are not going to get parallel answer. We need to reduce it to one answer. So there are certain set of problems that uniquely suit this quantum computer, and the sweet spot here is optimization and simulation of physical systems. And there are a lot of use cases that are currently also showing promise in optimization. Devika will cover in her topic extensively, right? So this is the and this has application in across industries, right? In financial risk modeling, in healthcare, in pharmaceutical industry. So this has application in traffic optimizations, in electrical system, where you can produce more the systems more efficiently. So all of this has application across industries and has to be, you know, we should choose the correct problem for the quantum computer. That is very important. So let's see the Azure Quantum overview, right? So in Azure Quantum, there are two sets of topics that we do here. See, one is optimization and one is quantum computing, right? What is the difference is optimization is Microsoft has done a lot of research. There are research engineers who build this optimization solvers and they make it available for you on Azure Quantum, right? So this can be utilized directly from Python SDKs that you can encode in your Python program currently, and you can use the pre-built optimization solvers on Azure Quantum, which runs on classical computers. So this gets inspiration from quantum computing concepts, but it runs on classical computers today. And there has been a lot of, proven case studies that Microsoft has published along with their partners, where that optimization is yielding, quantum optimization is yielding better results today. So in a nutshell, quantum optimization today is running on current classical system, and it is quantum inspired algorithms, and it runs on current classical systems. In quantum computing, when you see this Q#, right, this is quantum SDKs that are built to run on quantum computers, right? You can test these quantum executions today. You can formulate algorithms, and you can, there are standard libraries in chemistry, machine learning, and numerical library, which in Q#, which you can utilize. Yeah. Anybody had any questions? Yeah, if you have any questions, please feel free to stop, or you can put it on the chat as well. So this is the Q# is quantum execution that is you know, aim to run on quantum hardware and aim to design algorithms that get speed up by that are more efficient on a quantum computer, right? So so you will see a deep dive example on both of these today. So optimization, Devika will take us through an actual optimization problem and how we can run it on an quantum. We run it using a quantum inspired algorithm that is built by Microsoft on a classical system today using an Azure Quantum interface. And same here with Q#, you would see Amit Kumar taking us through this quantum execution, a sample, how an algorithm provides the speed up, and how you can run them on a quantum hardware via Azure Quantum today, right? So both of these options are available in Azure Quantum. When you provision an Azure workspace, Azure Quantum workspace, you can run optimization problems on the same, and you can run quantum computing problems on actual quantum hardware provided via the cloud today. So today we have IonQ and Honeywell providing as Microsoft partners, providing this hardware ecosystem. Through the cloud, you can run the quantum programs on their systems. So this is the deep dive workshop that we are going to see today, right? As I mentioned, so you can write Q-sharp programs, and Amit will be taking us through this in extensive detail in the next session, right? So and we also have, so this is not just Microsoft, like as I mentioned, partners like IonQ and Honeywell are putting their quantum systems on Microsoft via Azure, right? So that is partners, and there are also university research partners that we have today with Microsoft, and many open source contributors, customers, and affiliates who help us build this quantum journey, right? So this is this ecosystem of people who are invested in quantum. So after this, let's try and understand some basic concepts of quantum computing. Why this is important is, see, we saw two things, right? Like quantum computing, Q-sharp program, and optimization solvers. To understand the current algorithms that provide exponential speed up on a quantum computer, and to devise some of your own, we would need to understand that understand the basic concepts of quantum. So that is when we can understand how this exponential speed up is getting provided, and how we can also utilize the same, right? So so let me just quickly take you through this. So it's some level mathematical understanding as well, because quantum is in the very early stages. We need to understand from the very basics how everything works to get cracking on a quantum algorithm, right? So quantum systems, if you see, they are like you might have heard, right? Quantum is microscopic representation, right? So any quantum system is described by a Schrodinger's equation, which is actually a wave function. And see, that's enough physics for us to understand to go to the algorithms. But just to put the mathematical concept for you, so it is primarily any system is represented by a wave function in quantum. And like I described before, it is a probabilistic amplitude, right? Quantum systems, computers are intrinsically probabilistic, right? So it is not a deterministic system that we see like in a classical computer today. We have to understand the probabilities. At any point in time, the qubit, when put in a superposition, is in a probabilistic state, right? We describe, that's what it's right. It says we describe bits by the probability of finding their state when we observe them, right? So these are important concepts to understand in a quantum computer, right? So let's get started. On a classical computer, we had a bit, so it is 0 or 1, it's a scalar. But in quantum computing, we have a qubit, quantum bit, which is represented by a vector, okay? So if you say 0, it is not 0, it is 1, 0. 1, 0 in the sense, how we can try to understand is the probability of finding the qubit at the 0 state in 0 is 1. So it is 100%, it is in 0 state only, right? And in 1, it is 0% probability of finding it in the 0 state, but 100% probability of finding it in the 1 state. So that is how quantum numbers are represented. So 0 is 1, 0, and 1 is 0, 1 is the representation, right? And if you see this kind of let me put my pointer. This kind of a vertical line and a opening bracket, right? So this is called a Ket notation. So this Ket notation will be indicates that we are talking something quantum here, and it is not pure vectors, right? And that is what is said, like whenever we represent a qubit in superposition state, it is in some probability of finding in a 1 state and some probability of finding in a 0 state. And these two, since they are wave functions, they are probabilistic amplitude. Okay, probabilistic amplitude. So where this C0 squared plus C1 squared is equal to 1. So that is that is we would know, right, that the probability has to sum up to 1. Because these are probabilistic amplitudes, the square of them should always sum up to 1. So this, if you understand, is the probability. C0 is is a probability amplitude, but it corresponds to the probability of finding a qubit in the 0 state, and C1 is the probability of finding the qubit in the 1 state, right? So this is how you would represent a qubit in superposition. Okay, so let us go further and understand this in a geometrical representation, right? So in a geometrical representation, see, 0 here is in the horizontal line and 1 is here, and these are all superposition states. Okay, the superposition states have some probability. This is equal probability. See, because it has an equal probability of going into either a 0 or a 1. But it can have unequal probabilities as well. This is an equal superposition. What we say is an equal superposition state, where it has an equal probability of measuring as either 0 or 1, right? So this is the superposition concept in a geometrical representation. Actually, this is just an introduction here. Qubit, the Bloch sphere is the actual geometrical representation of a pure state of a qubit. Why? Because in any wave function, right, this C0 and C1 can also be complex numbers. So that so a sphere is the correct way of representing a qubit. But we are not for now. We are taking out the complex bit of it, and so we are removing the I part, and we are trying to understand everything with real numbers for now, right? So just to have the concept in mind, complex numbers are also absolutely possible. But to understand the concepts better, we are sticking to real numbers in this, right? So here, if you see, this is the unit circle representation. As I said before, the vertical and the horizontal lines are basis states, that is zeros and ones, and all the rest are superposition states. So let's try to understand how we will manipulate a quantum system, right? See, in classical computers, whether we realize it or not, there are logical operators that are gates that are acting on our bits, right? So, so you have a NOT gate in a classical computer, which is which will flip your bit, right? Similarly, in quantum computing, a qubit is a vector. So how do you manipulate a qubit? By using a matrix. So any gate in quantum computer is represented in a matrix format. Okay, so that is so that we can manipulate the qubit, and we can derive outputs, algorithms, all of this via representing qubits and manipulating them via the various gates available in quantum system. Okay. So similar to quantum computing, these are classical operators or 1 bit. So it is translated to quantum for you. See, if you see identity, this is the identity matrix on a qubit that is in 0 state. So identity matrix, as you may all know, gives the same back again, right? So this is 0 and it gives 0. This is 1 and it gives 1. This is negation, which actually flips it. So this is the negation matrix, and if you see 0 becomes 1 and 1 becomes 0, and a constant 0 and constant 1 functions, which irrespective of the input will give you a 0 or a 1 only as the output, right? So these are all matrix operation available. So another important concepts to understand quantum gates is it should be reversible. So given an operation, we should be able to find out and the result. So we put a gate on it and we get the result. We should be able to derive the input. So that is very, very important in a quantum. So quantum gates must be reversible. See, there are some classical operators which are not reversible. Like if you see in our previous example also, identity and negation are reversible, but constant 0 is not reversible because it always gives 0 as the output, right? Then how do you know what is the input? It actually modifies, it actually erases that information. You do not know what is the input. So we quantum gates have to be reversible, right? So that is when we can figure out what was the input given to the same. So these are the most popular quantum gates. One is this identity gate that we saw. So that is it, what the input is the output. So if you want to find out what was the input to a particular quantum system, you apply the identity state and get the output. You have to have the same output, right? So this may seem like not very useful, but these are very, very useful in representing some algorithms, right? Identity gate. The next is bit flip gate, which is actually it, or the NOT gate that we saw, right? So one becomes, see, this is a very useful geometrical representation for us to understand. 1 becomes 0, 0 becomes 1. And this is because it is the same, it is in equal superposition. What happens is, even if you apply the NOT gate, it remains in the same superposition, right? And here the coefficients are exchanged, right? The coefficients are same, but here if you see, the coefficient will be exchanged for 1 and 0. So that is the flip gate, right? The NOT gate or the X gate, as it is called. Next, we come to a very important gate in quantum system called the Hadamard gate. Hadamard gate, if you see, this is a mathematical representation of the same, and this will put your qubit in equal superposition, right? So if you see here, 0 state is brought to a state where there is an equal probability of getting either a 1 or a 0. So if you have to mathematically understand it, sometimes it is very useful to mathematically understand a gate. You can just multiply this with the representation of the qubit vector and get the output. So if you get the output, you will get 1/2 and 1/√2. That is the qubit in equal superposition. So from a basis state, that is, it is in 0, and we are putting it in an equal superposition. To imagine a coin, see the coin is in a head state, and when you flip it, you are flipping it, and you are putting it in equal superposition. You are putting it in a state where it can be, where it has a 50% probability of going to 1 and 50% probability of going to 0, right? And this is what is putting the qubit in equal superposition. So Hadamard gate is a very important gate, and you will see it applied in most of the quantum algorithms, because superposition is what gives, and with combination with other concepts in quantum computing, is what gives the exponential power to the algorithms, right? So if you see here, if you apply it to a basis state like 1 or 0, it puts the qubit in equal quantum superposition. And if you apply it back, if you are applying it on a superposition state, you get the basis state back. So it is reversible also. That's why we are using it. So if you put, if you apply it on a qubit that is in equal superposition, you will get the basis state back, right? So that is the Hadamard gate, and I'm sorry, I should have introduced this to you. So this is called the plus state, right? Plus state in the sense where it is in equal superposition of both the equal superposition of equal probabilities of going into a 1 state or a 0 state. Then it is called a plus state. This has also a separate notation in quantum computing. And this is called a minus state, where the one probability is flipped. That is, the face is flipped. Okay. So if you see here on the bottom quadrant, your second coordinate will have a negative sign. That is called the phase flipping. That is, it is rotation around the z axis, which we will see shortly. So when you put 0 in superposition, you get the plus state, and when you put 1 in minus position and 1 in superposition, you get the minus state, and so on, and reverse way also, right? So that's, now we are coming to the next gate. So sorry, this is a sequence of series of mathematical explanations, but we need to understand this so as to get to algorithms and graph algorithms that Amit will explain to us in the next session, right? So this is called the phase flip gate, right? This phase flip gate, what it does is it rotates around the z axis. So this is the z axis. If you imagine, this will make, it will not touch the coefficient on the of the 0, but it will flip the phase or flip the sign of the second coefficient. So if you see here, 1 becomes -1, and so plus state becomes minus state, and minus state become plus state, and so on. Okay, so this is the phase flip gate. So all of this can be mathematically deduced by doing matrix multiplication, a simple matrix multiplication, and then getting the state, right? So another very important concept to understand in classical versus quantum computing is the idea of measurement. So in a classical computer, a series of bits is there. When you are going to read it, it is not going to change the behavior. It is continuing to go be 0 and or 1, right? But in a quantum computer, when you measure a qubit, when it is in superposition, you are like observing the state changes it, because you are forcing it to measure either 0 or 1, right? So see, is the same classical example when you're flipping a coin, but finally when you want to measure it, you put the coin down and the coin settles to either 0 or 1, right? So when you are measuring a qubit in superposition, you are actually changing the behavior of it, and you will get the basis states, either 0 or 1, right? So so what is the probability that we'll get either 0 or 1? We'll get the measurement result 0 with the probability of C0 squared, where we represent C0 and C1 here, right? And the result 1 with the probability of C1 squared. So that is what is the probability that we get it. So when we say it's an equal superposition, so it is 50% probability of getting a 0 or a 50% probability of getting a 1. But the very important concept to understand is, when we measure it, we change the state of the system. We force it to measure out either 0 or 1, and whether we get 0 or 1 depends on the probability distribution, right? The probability of we getting what was the probability of the system earlier, which was higher. If C0 was higher, we have a higher probability of measuring a 0. And if C1 was higher, we have a higher probability of measuring a 1, right? So this is why in many of the quantum usages today, you will see that it is not just a single measurement. There will be multiple measurements, and this frequency distribution will be consolidated, right? Because we need to know, like, if there is a, if this is the state of the system, even if C1 is very less, we still have a 1% probability of measuring a 1. So it is not with one measurement. Sometimes there is thousands of measurements, like series of measurements, and then we get the probability distribution of what is the end result. So this is an important concept to understand. From a deterministic thing, we are going into a more of a probabilistic area with quantum computer. And this is a QSharp program that shows the measurement, and Amit is there to take us through this in detail. And so I'm giving this part to him. And then I want to briefly mention what are we have. See, we were till now talking about one qubit and single qubit gates. There are also multi-qubit gates which can be expanded to multiple qubits, right? So as you may understand, the 2 cross 2 matrix can only do on a 2 cross 1 vector, right? Can only manipulate a 2 cross 1 vector. So all we saw before are single qubit gates. There are 2 qubit gates as well, like the C0 gate, which are 4 cross 4, right? Depending on the size of the system, right? So, but we can, the most algorithms use single qubit gates on multiple qubits individually and then deduce. And there are also multi-qubit gates that you can benefit from, right? The C0 gate is a very powerful gate that we use in algorithms as well. So here, if you see 2 qubit representation, the same thing. This is a Ket notation that we saw. So again, in a 2 qubit world, there are 4 combination of results, right? So it can be 0, 0, 0, 1, 1, 0, or 1, 1, and each have a probability associated with it, probability amplitude, and the sum.
That's the only name I recognize.
Reena, you had any comments? Okay. Hello?
I did not have any comments, but looks like somebody was trying to speak.
Okay.
Or it could be just somebody who is just joined. Please put yourself.
Sure. Yeah, that could be the
trying to speak.
case.
Yeah.
And if you had any doubts, like please feel free to ask, or you can put it on the chat as well.
Yeah,
So,
I would recommend put on the chat, and then we will pause, ask Divya to pause and answer your questions.
Sure. So you have sorry, I lost the flow, the 2 qubit system as well. So where we have 4 combinations that can occur, and there is a probability amplitude associated with all. And like we said, the basic mathematics applies, right? So all the probabilities should sum up to 1 here, because they are probabilistic amplitudes that are associated with the wave function. Their amplitude square should sum up to 1. And the same for a 3 qubit system. Even if there are 8 configurations, the sum of the square of the probabilistic amplitudes should equal 1. Okay, so this is how we can mathematically understand a quantum system. And then there are other 2 powerful concepts that I want to introduce you to. So interference and entanglement. So interference is what, like as I was telling before, quantum system should be understood more on a wave principle, right? So you have constructive interference, that is, if 2 waves add up together, the amplitude increases, and destructive interference where the amplitude of the resulting wave decreases, right? And there is the concept of entanglement. Okay, entanglement is what Einstein very famously called a spooky action at a distance, right? Because entanglement states that if two quantum particles are entangled, by knowing the state of a quantum qubit at one end, you will be able to predict what is the state of the quantum qubit at the other end. So this is the basis of secure quantum communication and all of this. So some quantum states are impossible to factor into individual qubit states. So it means that they are entangled. The 2 qubits are entangled, and there are specific gates that we can apply to put a qubit into an entangled state with another qubit. So even if you take the qubits apart, now their states are entangled. So they will either show a positive coherence or a negative coherence. So this is the concept that makes quantum computing more powerful, because it entangles qubits and helps us model more complex systems as well, right? So sometimes it is very, very useful in quantum computing to understand this mathematically. So if you see here, the interference is quite easy to understand in terms of this is a qubit in superposition. It has equal probabilities of going to 0 state or 1 state. And then you have another qubit which is phase flipped, right? So if both of this interfere, what will happen? We can easily see that 0 is going to be the result, because this is going to cancel out, right? This is the concept of interference in a mathematical representation. The same way, entanglement can also be modeled, right? So if there is a multi-qubit qubit system that can be separated into two individual states, then it is separable state. But there are states like Bell states that cannot be represented in this fashion. If they cannot be represented, then it is in an entangled state. The two qubits are entangled, right? So this is the concept of entanglement as well. And here there are specific algorithms like Josa algorithm that we will see Amit take us through, and Shor's algorithm, which show exponentially faster performance when compared to a classical computer, because they utilize these concepts like superposition and interference, right? And there are quantum teleportation, quantum dense coding that actually utilize this entanglement principle to have a very, very secure communication. Okay, unless you have the other first qubit, you will never be able to tell. You can communicate very securely to the holder of the second qubit, right? So that is the concepts that are utilized in systems today, and these are some of the algorithms that provide exponentially faster speed up. And where are these getting utilized, right? So proposed quantum applications. So these are the proposed quantum applications, and some of which are very, very powerful for us, because they can help design new catalysts in an efficient manner, design better batteries, eradicate diseases. So there is a lot of promise. And you can see in quantum algorithms, zoo.org, all of these algorithms, the algorithms that provide quantum speed up for these applications already done. And if you want to explore, you can go and explore there. I would also like to show you where we are seeing promising quantum algorithms applications, right? These are all more further away, but these all show currently much better promise. And there are a lot of algorithms already which have been developed that are showing quantum speed up today. And why are people investing today? So once quantum algorithms are being developed, when our quantum systems become powerful enough, some of these we can run, but not all of these at a scale that we would require. When we have these quantum systems ready to run these algorithms and a scale we'll require, we will be able to make a lot of progress on all these applications, right? That is why there is a lot of research by companies like Microsoft, who are where a lot of bright people are putting a lot of their efforts into designing these algorithms and applications. Here we have I know that you all have taken out time on a Saturday to learn this. Where can you explore better, and how can you contribute? This is quantum is something for the future as well, and how can we equip ourselves better and know the things that are cutting edge right now and being developed now. So what we have is you have a lot of scope to get involved here. See, if you want to go deeper dive, there is an excellently done MS Learn set of links that we can pass to you. You can join the Q-Sharp community. Q-Sharp is open source. The quantum execution language that Amit also is going to take us through is open source, and you can contribute to its development. You have Azure Quantum, where you get free credits to explore Azure Quantum. That is, you get almost $500 free credit, free execution credits on each of the providers like IonQ and Honeywell today. So that is a lot of scope. You can do a lot of exploration on quantum algorithms there. And on the free basis, you can also, test quantum optimization solvers that Devika is going to take us through in this workshop. So please stay with us and explore this Q-Sharp and quantum optimization algorithms. And there is also a very excellent learning material called Quantum Katas, where there is Python notebooks online that you can try quantum programs, and you can understand each of the concepts that we were talking about, right? How to apply them. So all of these links we will pass to you by the end of this workshop, and please feel free to explore more on this. And thank you very much. Now I will hand the control over to Amit, who will take us through Q# and an algorithm for a sample, right? Yeah. Thank you very much. If you had any questions, please you can ask us now, or you can continue to put it on the chat as well. Sure. I think. Yes, there is a question by Bishwoth saying, can we have a situation where superposition is there among qubit but no entanglement? Yes, it is perfectly possible to have a superposition without entanglement. So there are certain gates, like I was telling you, a H gate, if you apply, your qubit is in superposition. But you need not put the qubits into entanglement. So if you apply a H gate and then a C0, the qubits go into entanglement, but it is not necessary or needed for all the algorithms, and it's an option only. Okay, I think any other thing, please continue to put it on the chat. Amit, are you here, please?
Yeah, I can hear you. Can you hear me?
Yeah, I can hear you. I think I can hand it over to you from here to take us through Q#.
Sure. Give me a second. Okay.
There's one more question in the meantime, if you want to answer, either Amit or Divya.
Yeah,
How
qubit is represented physically.
Yeah.
See, that is where there are there are different approaches to it. It is not like a classical bit, or it's not a one standard approach. See, Microsoft is going for a topological qubit. That's that you can imagine as an electrical wire with an space at the very ends. And also there are superconducting ions conducted, ions suspended in electromagnetic fields. So those are the approaches that industry today is, taking to approach a qubit. So it is not standard. There are a lot of experiments going on there. There are a couple of representations that are more popular, but it is not. And all of these, the standard requirement for all of this is keep a qubit in a very cold temperature. It is put. That's why you see all the hanging structure when you see a quantum computer. It's a refrigerator where these ions are suspended in an electromagnetic field, or this electrical wire is suspended. So all of this are kept in a refrigerator in a very cold space. So I hope I at least gave you an idea of how this is done, right? So this is still an area of active research. Okay, thank you. Amit, over to you, please. Yeah.
Are you having difficulty sharing? Is that an issue?
Yes, entanglement happens. Yeah, entanglement only pair of two qubits, not necessarily. It can be multi-qubits. Multiple qubits can also be put under entanglement. So 2 or more qubits.
Yeah, I was waiting for the answers to be.
Okay, no worries. Yeah.
Can I
Hello.
start sharing, or is there any questions in the meantime?
Yeah, I have a question.
Yeah, sure.
I mean, I wasn't in the first part of the lecture, so you have been speaking about optimization. So, what kind of optimization are you talking about?
See, quantum optimizations, Venkat. So I'm not sure if I'm getting your name correctly, but please hang on.
Yeah, it's Venkat.
Yeah. Devika here is going to take us through an optimization deep dive. So she will outline what are the optimization problems that will better fit a quantum optimization solver today, and some quantum optimization solvers that are available via Azure Quantum that you can use. So she will take us through that. So that is coming just after Amit's session. Yeah, thank you.
Yeah, thank you.
So you are able to see my screen,
Yeah, yes, Amit, yeah.
the presenter mode or the audience mode?
Audience mode.
Okay.
It's good. Yeah.
So I think I can get started. All the questions are right.
Yeah, sure. Please, thanks, Amit.
Okay, so yeah, thanks, Divya. In fact, thank you for giving a quick introduction about quantum. And as Divya said, some of these concepts that we have discussed in quantum, they will be useful for us to proceed forward. So now it works. Yes. Okay. So let's continue on that. So the concept of superposition and the concept of the concept of qubit and the different states like superposition, entanglement, whatever we discussed, all these concepts will be useful for us to proceed in the journey of understanding more towards quantum. So what we are going to do, we are going to start on the Q sharp now and learn that how this is a specific thing will work and all those things. Okay, so let me. So this is a slide that we have seen earlier. So there are two major things. Like Azure Quantum applications actually are into two categories. One we call quantum optimization and quantum computation, and this is what we have already seen with Divya. Now this is the portion that we are going to cover today in my session, which is quantum computing. So computing and optimization are two areas which today Azure Quantum is targeting to solve. Right? Computing is something where you actually implement algorithms that are designed for quantum hardware. Not all the algorithms need a quantum hardware, but yes, some of them are there where we can leverage the quantum hardware, where we can solve the problems in a much faster way compared to the classical computers. And optimization is also having, it's like where you actually solve some optimization problem, and there are already many solvers that are present, some of which will be discussed in the next session, and you can use them there. Okay, so I will be focusing mainly on quantum computation, and quantum computation is basically focused on different algorithms. And application for quantum computations are developed in Q sharp, and that can be run on hardware and simulators using Azure Quantum and Quantum Development Kit. So there are two things. One is Azure Quantum and QDK. These are two things that we have been talking about. I'll slowly go through in each one of them. Now, if you go deeper into this, we have three things. One is how do we learn it? Second is how do we code it? Third is what are the libraries that are available to us for use? So if you want to learn, as Divya covered, Kata's tutorials are there. I will give you the demo of that, how to go there and see that. There are code samples into it, which you can see. There is MS Learn, where you can go and understand more about Q sharp language. Then where do you code this? We code it either in Visual Studio, which is VS written here. Let me take a pointer. This is VS, which is Visual Studio. Then we have VS Code, which is Visual Studio Code. And this can also be coded in Jupyter Notebook. So the people who are more comfortable with Jupyter Notebooks, they can also try Q sharp code into Jupyter Notebooks. Then we can use libraries. When I say you can use libraries, there are multiple libraries that we will see during the discussion, that what are different libraries that we can use. Then once you have written all this, what all you do? you either can run it on your local simulator. So when I say local simulator, you can run either at your local machine that has a simulator after you install QDK, or you can run it on Azure Quantum as well. And even in Azure Quantum, there are simulators that can run it, or you can run that on actual hardware as well. And we will see some of those things today. Now, and if you have any questions in the meantime, please put them in the chat window. And I'm not able to see the chat window, so somebody can stop me and I can see into it. Otherwise, maybe Devik or Divya can also reply if they have the answers ready. Okay. Now, why Q sharp? So when we talk about Q sharp, it's a language, right? And how it is built from the ground up for quantum application development. Now, it was designed specifically for developing application for quantum computers, and the nature of quantum computers is built directly to the language and enhanced with additional libraries and high-level language functionality that is specific to the quantum applications. For example, like if you see Qubit in Q sharp is a data type. And quantum concepts like we have superpositions, measurement, entanglement, all these can be actually modeled through implicit side effects. So you can create a qubit in the code, and then you can apply different things to put them into either superposition or entanglement or measurement, right? And you can think of Q-sharp program as classical programs, the way we write classical programs that can send quantum instructions. In the normal way, we set the classical instructions like, okay, C is equal to A plus B. So we are adding the values of A and B into C, assuming they are integers. If they are strings, we usually concatenate them. That's the way classical computer work, classical instruction work of concatenation or addition, depending on the type of operator. Similarly, you can think of a Q-sharp program as classical program only. But here, what we do, we send the quantum instructions to a quantum device, where the quantum device is an accelerator for your classical workflow. Okay. Now, having been designed specifically with quantum execution workflow in mind, Q-sharp actually enables the automation of many classical tasks that are needed to make good use of quantum computers. Right. Example of this can be, for example, it can be an inverting sequence of instructions, a common occurrence in quantum algorithm. Right. So, what Q-sharp has done, it has built in functionality to automate this all set of classical instruction that you can focus to develop or create your algorithm. Okay. Now, all these design choices that are there in Q-sharp, it enables you to actually create applications that are optimized for execution on quantum computers. By how? By abstracting away many of the manual tasks that are required to go from classical program to quantum program. Right. So that is what the first benefit that we see here. The second thing, if you see, it is actually a hardware agnostic. So what is the meaning of hardware agnostic? So actually Q-sharp are optimized to run on quantum computers, and this includes quantum computers of different architecture, many different architecture, right? Today, when you develop application for classical computers, you generally don't worry too much about underlying hardware. Are you running on a Dell machine or a HP machine? Are you running on an AMD or your Intel? You don't bother too much about the underlying hardware. You just have a program and you have your executables and you run them, right? Similarly, the same things works here. So what does Q-sharp do? It provides the same level of hardware abstraction for quantum development. And in developing an application with Q-sharp, you will be able to run that application on a variety of quantum execution targets in Azure Quantum. Now, as hardware scales, so can your Q-sharp application can also scale, and you can run Q-sharp on hardware with Azure Quantum today and be confident that your application can scale on scalable quantum hardware in the future as well. So that's the way that we talk about actually, is it hardware agnostic or not? And the next one is build for scalability of development. So actually, Q-sharp is built with the scale in mind. Okay, it's actually a high-level language that is designed for quantum algorithm that we have already talked about, right? And you will be mostly familiar with the classical programming construct that you have already known, right? That okay, there is a class, or there is a operation, or there is a namespace, or there is a library that you have to use, and we will see some of that in an example now, right? So the high-level language abstraction like Q-sharp libraries and ability to share and collaborate on code create greater scalability of development and applications. And as you know, like quantum computers evolve and scale, so too will the complexity of applications we can and we will execute on them. And this could require using quantum algorithm from classical application. You can see what this looks like today by using the interoperability with classical language with Python and .NET language, right? So in creating Q-Sharp, this also has been very important to support the greater developer tools that are already on the market. So that's why it is integrated with Visual Studio. It is integrated with Visual Studio Code, with code spaces, as well as Jupyter Notebook. And these integrations actually take advantage of some of the great features that you are used to in these environments, such as code completion, code actions, and multiple other things, right? So let me take some libraries example, and these are libraries. So let me do one thing. I'll probably go to demo, and I'll show you some of that, and I'll come back to this. Okay, so that you can resonate with better. And okay, so let me go here, and I'll do one thing. I'll delete. So let me ask you one question to audience. How many of you have worked with at least one object-oriented programming language? Raise your hands. At least one. Maybe C++ is also fine. C#, C++, anything. Only one person? More? Nobody else? Please raise your hand. I'm not going to ask you any other questions. I'm not going to put you on a spot for committing to knowing the language. Okay, many of you. Okay, I see less hands still. It's fine, no problem. So let me do one thing. Let me. Okay, now you can lower your hands and tell me that how many of you are actually have worked on Visual Studio Code. You have used Visual Studio Code for at least some programs. Are you aware of that? Visual Studio Code, VS Code, short form. Okay, interesting. So many of them are knowing this. So what we are going to do today, that we are going to use the Visual Studio Code. You can see my Visual Studio Code window.
Yes.
Yes.
Okay, perfect. So what I have done is I have installed a Q-Sharp, and let me open a. I'll bring it and install QDK. Okay. Install QDK. Installation of this. So what we are going to do is we are going to install QDK, Quantum Development Kit, onto local machine, and that will help you to create the programs and run the programs on local simulator and all those things, and integrate with Visual Studio. So I have installed already onto my machine. So I'm just telling you the steps that how to do it. So you can just say install QDK, and you will get the links, and you can use those links in order to install any one of that. So here is the link where you can install QDK, and when you install QDK, you can install extension also for Visual Studio Code, and you can start working. So I'm pasting it in the chat window. Okay, cool. So this is a link which you can use to install QDK. And once you install QDK, so QDK, what is QDK? QDK is actually an environment. It's a quantum development kit which will actually install all the libraries that are required for you to write code in Q# and do basic things. Not basic, actually, even submission and everything is also done, right? So that is the way you can actually use QDK, and you can start working on it. So this is my Visual Studio Code window, and as many of you have worked with it, I'll try to go here, and I will say, once you are installed, if you have installed it, you will get all these templates with you. Create new project, install command line project templates, go to Quantum Development Kit, install Q. So I'm saying, okay, create a project. When I say create a project, I have multiple other options. Standalone console applications, quantum applications targeted to Honeywell backend, quantum application targeted to IonQ backend, quantum library, unit testing, and all those things. Okay, so these are the things that are all there with us. So if you are installing, I can give a minute and you can install, and we can move together, or I can go slowly and you can install in the parallels. Okay, so let me go here. and I'll key new project, extending application. When I say standalone application, I say okay. I'll go here and I'll create a project called. Okay, I'll go here. Demo. Live. Okay, create project. So I have created a project which is demo live. Okay, and let me delete this folder if I don't need this. I have. When I have a demo live project. Now, when you create a project in QSharp library, you will have something like this, where you will have bin object, and you will have demo live.cs project and program.cs. So let me move to the program.cs. Now let's understand a bit about that. What are all these constructs that you have seen? So when you move into this, you will have multiple things that you have never seen, because this is different language. Of course, the syntax will also be different. You will have a namespace, which is the highest level of collapsible item, and then you have some code inside it. Now, when you have some code inside it, you will have these different things. So let's go one by one. So what's the namespace? Namespace. So every QSharp file typically starts with a namespace, and what does it do? It actually helps you to organize related functionality, and their use actually becomes important when you use QSharp libraries into your program, and when you write your own libraries as well, right? And now what is this? These are all libraries. So the way you write import into some other language, you write open here to bring the libraries here. Okay. So now what is library? So actually QSharp makes extensive use of libraries. It's basically a library is a package, for those who don't know what's a library, that contains functions and different operations that you can use in quantum programs. For example, if you say Microsoft.quantum.chemistry, let me just write it. Open Microsoft.quantum.chemistry. Okay, it seems it is not installed here, but that's fine. I can take any other one. Let's say arrays. So if you take Microsoft.quantum.arrays, then it helps you to bring all the arrays related operations here into this specific program. If you write Microsoft.quantum.chemistry, then that will help you to perform all the quantum calculations that is related to chemistry. So there are several standard libraries that includes some sort of basic operations. Okay, when you call a function or operation from a library, you specify the library name, right? So for example, you can either write this, or you can write completely like Microsoft.quantum.intrinsic. Message, right? And you write a message. Let's say hello. That's it. So this is a short way of writing it. So you just take this and you import it, or basically open it here, and you are good to go. I have already done it, so it is going duplicity, right? It's already in use. Fine. I think you basically got the idea, right? Okay, so more commonly, what would you use? We use here a keyword called open, open directive to make your code more select and easier to read, right? Now here we have multiple of them, and we are using them here. Okay. Now here you can simply say a message, because you have already pulled it. Now next is operations. So what is operations? Now operation is basically, these are the basic building blocks of QSharp program. A QSharp operation is a quantum subroutine. That is, it is callable routine that contains quantum operations that modify the state of the qubit register. So you have a qubit register, and if this operation, whatever you write in that, of course, this is just printing a message. But in general, what will the operation do? It will actually change the it can change the state of the qubit register, or run all the code that is written inside this code block, right? To define a QSharp operation, you specify the name of the operation also, along with its input and output. So whatever you write here in this bracket, inside this bracket, it becomes your input, and whatever you write here, that becomes the type of the output. I repeat, the type of the output. This is a return type. Okay. So So QSharp library also provide operations that you can use in your program. Once one operation you will use later in this program is like Hadamard gate operation, H operation, and think of H gate operation as a way to putting qubit into a even superposition. Okay, once in superposition, a qubit has 50% chance of being measured as 1 or 0. So as it is told to you by Divya that once the things are in superposition, then the qubit can be either in 0 state or it can be in 1 state, but we will not know, right? So that is what we will see in some of the examples. Then comes your type. What is the type of thing? Okay, so let me write a basic basic code. So let me explain you some of this. That okay, what is this? So this intrinsic library is actually I'm using for gates, such as, and you will learn over time, Hadamard gate, Poly X gate, Y gate, etc. And this is also used for transformations. Transformations, what transformation? Such as rotations, etc. Okay. Now, when it comes to Canon, what will library do? This actually this contains a variety of useful operations. Variety of useful operations and functions. Okay, and let's talk about this. What is entry point? So entry point, basically when you see entry point, first of all, there can be only one entry point, and entry point tells the QSharp compiler where to execute a program. This is tells you, let's say you have multiple operations, then whatever operation is mentioned as an entry point, that operation will be called first. That's the way the entry points actually is understood here. It's put here. Okay. Then there are others also. For example, Microsoft.quantum.measurement, which actually helps you to measure something. So let me write that for an example. I will say open Microsoft.quantum.measurement. It will help you measure. Now, what is a measurement? The measurement, as Divya already told you, is actually checking the state of a quantum at any given point of time. Now, here is something important that you should remember. When you initialize a qubit in a program, by default, it is in 0 state. 0 or 1 state, 2 state can be. It is always in qubit is in 0 state. Until the moment you put that qubit into superposition, you can always measure it deterministically. But the moment you put in superposition and you try to measure it, you can never tell that what is its position. It can be anything, 0 or 1, because it is in superposition. Now, in order to know what is its position, you apply an operation called measurement. But when you apply an operation called measurement, it collapses to one condition, either 0 or 1, and it gives you the output of that. That is important to understand. We will talk about it again in a moment. Okay. So, okay, measurement. So when I say measurement, what is this? This is for measurement of qubit. Okay. There are many examples I can say, such as there is a M reset Z. So M reset Z. So for example, M reset Z. What does it do? M reset does actually it actually measures a single qubit in Z basis. And also resets it to a fixed initial state. Let me not write this. So we can measure a qubit into X, Y, or Z state, Z basis. And one of the example that Divya has showed you is the block sphere, where you can compare it in X, Y, or Z. Right? So that's the one that we can always remember. Okay, so far so clear. Any questions specifically, then we can talk about them. Okay, I'm not seeing, so I'll move slow. So let me start with the program. So what I'm going to do, I'm going to measure a superposition. Okay, let me write a superposition. So I'm writing an operation. Measure superposition. Okay, and I'm saying it's a result, and I'm saying the operation as this. Now, the first thing is use. So when I say use, it's like creating a qubit. I write like this. So what does it do? What this statement do? This statement basically, it creates an operation. Sorry, it creates a qubit. Okay, fine. Let me say return something. I'm just saying this so that it doesn't give you an error. So what does this statement do? It allocates a qubit, right, for use, and automatically, always remember, programmatically, when you do this, it is in zero state. You have seen this specific thing, that is the 1 second, please. So you can see this, that it allocates the qubit for use, automatically it is in zero state, and then you have created a qubit. Now we want to put this qubit into superposition, and then we wanted to collapse it to see what happened, right? So there is a gate called H gate, and how do you apply the H gate in code? You just say H and you pass the qubit, and that's it. So simple. It may take some time to digest the concept, but it is one line to actually put the qubit into superposition. Now, what does it do? It puts qubit in superposition of 0 and 1. That's it, just one line of code. And then I'm saying measure it. So when I say measure, I'm saying, okay, I'm reset Z, and what to measure? Q. That's it. I want to measure it at what is its value, right? So now let's discuss a little bit about things, right? So I have written one thing called results here. So it represents the result of a projective measurement into the eigenspaces of a quantum operator with eigenvalue plus minus 1. But if you don't understand, forget about this complex eigenvalue and eigenspaces. If you do not know that, then just understand it can result possible value of 0 or 1. Okay, and I have been interchangeably using two terms called operations and functions, but they are different. Operations are different, functions are different, but for now you understand them as callables. We can say them they are callable, right? And most of the QSHA files will contain one or more callable. So naturally, we need to let the compiler know which callable is to run, and when we provide the .NET some command, it will get to know. So this is a callable for now, assume, and this specific keyword will tell that this is the one to run initially. Okay, now let me use the command palette, not command palette. I'll say start debugging, and okay, install an extension for QSHA. It's installing. Give it a second. Configurations, launcher JSON is here. I think my environment is not working, so give me a second. Demo files is not there. Okay, NatMate is there. It is exe. Let's forget group also. Required. Add them. Yes. File save. Why it is coming again and again? I have set it up already. Operations. there anything in the thing that I'm missing? Check. Okay, I think it needs a configuration part. So I'll take the configuration from some other file and I will paste it. Okay, so this is a place with other configurations, and I say save. Start. So this is a not a random number. This is a demo random number CS. This is my demo. Okay. Fine. So I go here, I go to program, I go here, CS pod is fine, this is there. So now it's running and it's trying to get the DLL. Demo library. Okay. Fair enough. Let me open another program and see why it is giving me this issue. Internal console, workspace folder, attach. Oh, CS file is not there. That's interesting. CS file is there.
Amit, in your terminal, right? Go to this demo live project. It is in Microsoft QC demo quit key. So it is trying to run the project there. In your terminal, it is in this demo quit key. Okay. It has.
It is in bin.
Okay.
It is in right place. Net core app on. One second. I'm just trying to see that is it the file name is different or something, because the project property and everything seems to be right. And executable is fine. Task is also fine. Launching is also fine. 2.0 .NET console launch build. I think it is requiring a DLL which is not there. Demo live, but DLL is still not there. Fair enough. Then you have library internal console false. Okay, no problem. I have one backup project. I'll try running there. That's not an issue. 1 second. This happens in a live demo, so bear with me. It doesn't look like live. Fair enough. 1 second. So I'll open this. I'll keep this aside. And I'll take something else. See if the other one opens. It's opening now. So the same code, I can say that this is the same code written there. Okay, you can see that right now. Screen you can see.
Yeah, we can see.
Okay, so same code. We are just using MQ, and let me run this. No, I don't need survey. I don't need survey. Only the code name is different, so I will just run it. I will say .NET run. When I say .NET run, it will run the project and will give you 1 bit as 0. You see this? So what we have done, we have just written 3 lines: measurement, superposition, only one, and I have used qubit. I have created a qubit, which what is doing? It's allocating a qubit for use. It's creating the creating a superposition for that qubit and it's measuring. So, okay, so let me write it. Earlier I have written reset now. Set. I will say set. I'll say run. Okay, so I can run here, start debugging, and I'll run here. Either I can do this or I can run a command window called .NET terminal. So just bear with me for a second. It will come down here and it will show you the output as well. Let's build it. It's building. You can see the message in the down, and it says 0 errors and 0 warning. Fair enough. And then it will start running here, and it will give you 1 bit 1. So sometimes, since now I have applied the superposition, sometimes it will go to 0 and sometimes it will go to 1. Either of that, it will start moving. So far clear. So far this thing is clear. What it is doing, it is just actually creating a qubit, putting it in superposition, and running it here. Measuring it here. Measurement will cause it to collapse and either go to 0 or 1. Okay, cool.
Amit, what happens if you delete the HQ part? What happens to the M reset Zs?
I'll show you. You tell me what should happen.
See, in that case, then you are not doing any superposition, right? In
Yes.
that case.
Yes.
So that means it will always, you should give a deterministic value. I mean, always the unique value should come, right?
Which value out of 0 or 1?
So you had allocated qubit automatically as 0. So I expect always a 0 there.
You are right. Let me show you. So when you put this way, you are not putting it in superposition. It is always be 0. Okay. So it is just running now. It is building it again because I have changed the code. So I need to build it again. And when it is built, since I have written this code, it will show me in the 0. You see this?
Yeah. So another question, I mean, in that case, when you are doing this HQ, let's say, and sometimes you get a 0, sometimes a 1. So even there should be a probability between this 0 and 1, right? Is it like 50-50 kind of thing? Let's say if you do 10,000 times, do you expect around 5,000 times 0 around, I'm saying, and around 5,000 times 1?
You are absolutely right. When you do it on a longer shot, means multiple runs, you will see the combination reaching 50-50. Absolutely right. Right. But if you do it only one time, then it can be either 0 or 1, because in one or twice you cannot see the probability.
Okay. And in that case, it can something be done in the program so that I can make 0, let's say, as 30% probability and 70% as 1, so that if I run 10,000 times, I expect 3,000 as 0, 3,000 times and 7,000 as 1. I mean, can even those things be done?
There are some construct doing that, but that way you are actually not exploiting the real undeterminism and parallelism of superposition within quantum. You are forcing it to go that probability that you want to make it happen. Okay, so possibly yes, theoretically yes, but practically no. If you put an Hadamard gate, internally it can be in any superpositions, and through gates you can change the phases and etc. But actually it will be in 50-50%. Now when you collapse it a single bit, what will happen? At that point of time, whatever is the superposition, if the probability of 1 is higher, towards higher side, it will show you 1. If the probability is on 0 side, it will show you 0.
Okay.
Okay, cool. Thanks. So I am now putting it in superposition, and I can say, let me go here. I can show you a couple of times. .NET run, and I can show you .NET run. See, and I will run it a couple of times so that you can see sometimes 0, sometimes 1. All the time it's coming 0, because I think I have not built it again. Let me build it again. So when I'm building it, I have uncommented that code. So now the HQ is enabled, and the bit will be put into the superposition. So when it is built, it is run, you will see some value 1, good, and I will run from there. .NET run. Sometime now it will come 0. Sometime
coding it up.
.NET run. You see, sometimes 0 is coming and sometimes 1 is coming because the mouse superposition is there. Okay, Cool. So let me move forward. Very basic program, no rocket science, nothing complex, nothing like that sort. Okay, I have not done anything specific of that nature till now. Okay, now this is about 1 qubit. Now let me move to go slowly onto the from only 1 to I can go to to, let's say, take an array of few qubits. Okay, and I say that I will give a number which is within my n, and it will be integer, and I want results to be also an array. Very simple. Again, I am taking the qubits now, but now there is no 1 qubit. I have to take the n because the n is there, and there is a as you have the loops there, here also you have something called apply function. So I say apply to each. Here is apply to each. Let me type it. Apply to each. Now what you want to apply to each? To each qubit, you want to apply the H gate, and you see qubit, and you see qubits because you have qubits. And let me take this to make it more simple. Qubit, it's qubits, and then you say okay. So what it is doing? It is applying H gate to each qubit in the register, right? Okay. Now, when you have done this, you don't need this, and what you will return for each of this? What will you return? You will have to apply the other thing also. So you can say for each. And for each you want to apply, let's say MD set Z to each qubits. That's it, you're done. So in the previous program, I have done only 1 qubit. Here I have done a couple of qubits, more than 1 qubits. Okay, cool. So let me go here. And it is measures each qubit. Okay, and returns result. Okay, and returns the, let me say, result array, because we have the array, right? We have the array. Okay, cool. Now let me build it. So I go here, I say run, I say start debugging, and I am running this. So when it is debugging, it will start creating the build for this, and during the build will do, right? So far this article has only considered an operation that takes no input, the previous one, but here you are taking some input also. And now what is that input? That input is actually that input is the value, that how many qubits you want to run. The program has exited. Okay. Good. Did not come with the run. Run. .NET run, and now I say n is equal to, I'm passing a parameter that 4 qubits it can get. Yes, so it has created 4 qubits, and you can see the output as first is 0, second is 0, third is 0, and fourth is also 0. Okay, let me try again. Some of them can be 1, some of them can be 0. You can see now 3 of them are 0 and 1 of them is 1, right? So what it is doing, it's actually, here the returned value is actually an array of measurement result, right? So you can see that these are different constructs. Apply to each is 1, for each is 1, and this is what we have added for apply to each. This is defined in Canon library. For each is defined in arrays. So in the array I have I want to do for each, so I am doing it. But when you want to apply a gate like Hadamard gate, you need to use the apply to each. Don't worry if you don't remember all these syntaxes, this will come slowly, and you can see the Microsoft documentation which is publicly available in order to understand what each one of these do and how to use them. That's not a big deal. The big deal is to understand how it is working internally and what is the concept. So I can run a couple of times and you can see the detailing. See, one now the first qubit is in collapse to 1 and rest of collapse to 0.
So Amit, here apply to each when you say this capital letter H, this is the Hadamard gate, right? H stands for that.
Yes.
So this is a keyword, right? It's not a variable which you are taking it from Microsoft Quantum Canon.
It is so it is a keyword. Yes, it is a gate. I'm applying a gate. When I say apply to each, so if you go to apply to each, the first parameter you can see it's an operation. You see single element operation.
Yeah.
If I hold the mouse here, you can see the single element operation. So the operation can be applying X gate, applying Y gate, applying Z gate, applying H gate, applying C naught gate, any gate onto what? Onto the second parameter, which is qubit.
Okay, so here only you can actually switch to different gates and rerun the program and get different kind of outputs.
Yes. That's the way it works. You're absolutely right. I'm just showing you that how superpositions can be created and individual things and all those things. Is so far so clear?
Yeah, I mean, fine.
Perfect. Any other questions you have? No? Okay, good. So I have not jumped into my agenda actually. I'm just trying to make you understand and comfortable with the Q-Sharp program, basic structures, how to run it, how to see this, how to apply, what are the open construct entry points, operations, functions, apply to each functions, namespaces, and environment. Now I will slowly go into random number program as well. That's what we wanted to cover today. Okay, so so this is the way we pass parameters also. That is what we have learned. Now something really interesting that I wanted to introduce you, and you can go deeper into it later. So when you pass this parameter, there is some more parameters that is called resource estimator. This estimator. When you run with this thing, resource estimator is a parameter that when we pass during the run, it actually tells that when this program is running on simulator or when this program is running on actual hardware, how many different kind of resources internally this will require for all the operations to perform that you have mentioned in the program. Let me enter. Now, when you say this, resource estimator could not be found. That's also interesting. I'm getting many surprises. Okay, so let me go here and I will show. Okay, so I'll come to resource estimator because it seems default simulator object property is not there. Okay, so resource estimator is not there. Simulator is there. Simulator also not there. -4. 1 second. Let me add it. If it doesn't work, I'll show you the Azure simulator. That's also fine. Did I do this? That's giving issues. So, okay. Even if it doesn't come, I'll explain you what does it mean. It actually estimates the resources that is required to run the given instance. The build failed. Let me run build again. Start debugging. Okay, and it will actually tell you that it's, so there is a library called Quantum Trace Simulator, and in the Quantum Trace Simulator, you will see that how this is going to be run. Okay, so let me do one thing. Let me go back to PPT and show you something and come back on the Azure part. So how many of you have you actually tried things on Azure Quantum? Sorry, Microsoft Azure. Have you opened Microsoft Azure at any point of time and seen that how does it work? What are the internals of it? What is the namespace? What's the resource group? What's the subscription? What's the resource? How do we create a resource? Any of you are familiar with Microsoft Azure? Raise your hands. Microsoft Azure. No? Okay. So let me do one thing. I will first let you take there. I'll come to resource estimator. Let me take a note what is remaining. Let's print resource Estimator. I will take this up before I leave so that I explain. Okay. So anyways, so let me go here. If you're not familiar with Azure, I'll just quickly showing you how does it look like. So this is my Azure portal. You go to portal.azure.com and you try to open the Microsoft Azure portal, right? Now in Microsoft Azure portal, you have different things. So how does it, do I have a slide? One second, let me check if I have a slide somewhere that can help you understand. Okay. Do you see this window, Azure subscription components? Do you see the PPT?
Yes, Amit.
Okay. So in Azure, you have subscriptions. I have subscription in Azure. And then within each subscription, you have multiple resource group. And then each resource group is a logical combination of some resources. Now, assume that you wanted to create a database in cloud. You create a database resource in the resource group. And if you have to create a compute, you create compute in the cloud. That compute is a resource. Or if you want to VM, virtual machine in the cloud, you create a VM as a resource and put it in the resource group. Now, a resource group is actually a logical collection of different resources in the cloud, where a logical collection represents usually a project. So when I work in a project, I create a resource group for that project. And all the resources that are required for that project, I keep that usually in that resource group. That's the way logically it is collected and stored. Okay. So when I go here and I show you something, let me show you the subscription. So if you see here, you can see that this is my subscription and I have other things also. And in this subscription, I have multiple resource group. So let me go to home. This is home and I can create a resource. So you can navigate to subscription. If you click on this, you will see what subscription I have. So I have one subscription as of now. This is my subscription ID. This is my role. And this is my current cost and it is active subscription. Okay. Then in this, I have resource group. So how many resource group I have in this subscription? I have 3 resource groups, Azure Quantum and other resource group as well. Now, if I go to the first, this resource group, let me go to home. I can click on all resources and I can see all the possible resources that are there. So how many, I have one subscription in this that is attached to this email ID. Then under that, I have multiple resource group. And under those, these are total resources. So for the purpose of this demo, I have created a QETCI resource group. But creating a resource group is simple. But so let me explain you. I go to a resource and I type here Azure Quantum. So let's say you wanted to create a Azure Quantum service. So you go here in Marketplace and you can create this one, or you can go to Quantum Workspace. I have to create a workspace. So I'll create a workspace, Quantum Workspace, and I click this. So first time when you create, you can create a Quantum Workspace. And how do you create? You click on create. And when you click on create, it will ask you a few details. Now, what are the kind of details it will ask you? It will ask you that, okay, you want to go a quick create or advanced create. I'll say, okay, I want to go advanced create. And then you need to give some details. So for example, subscription is automatically selected. And then you give a resource group name. So I already have resource. You can use that. If it is not there, you can create new and you can give the resource name. Okay, then you give that what is your workspace name. In my demo, I have given QETCI demo. You can write anything. And it tries to see whether this specific name is publicly available or not. If not, it will discourage you. Then the reason. So as every cloud is actually every cloud is deployed into multiple regions. Similarly, Microsoft Azure has multiple regions, and these are the regions where Quantum Workspace is available. Now you don't see India here, but Azure is in India also. But for many services, but for Quantum, some of these data centers you have to use, because that Quantum Workspace can be created only in these data centers. So you can select that. Then you can say, okay, storage account. So why there is a storage account? Storage account is needed so that all your results, output, experiments are stored into that storage account. And then you go to next. Where in the second phase, you see providers. Now, when you want to run your quantum program, you would want to run on two things. Either you run on simulator or you run on actual computer hardware. So Microsoft has partnered with multiple companies. For example, IonQ, Quantum, One Cloud Optimization, and in fact, Microsoft itself is having some hardware. So you can choose that on which quantum hardware, actual machine you want to run your program. Okay, and then once you select that, you can come here and you can review and create. Okay, so you will see some pricing also here that these are free as of now for quantum computing, but this is usage-based pricing for optimization. So this session is for quantum computing, so I will be using these free credits to show you something. Okay, validation failed because I have not given the details here. If you see in the basic, I have left that case because I already have one. So let me go back. Let me close this, and I will use this specific quantum workspace which is created for me. So if you go give those details, this will be created and you will see the window something like this. Okay, now this is my quantum workspace. So if you see, let me tell you what we have seen. We have seen that there is a subscription. Subscription contains resource group, and resource group contain where we create the quantum workspace as a resource. Okay, and in that, once you create that, you start submitting the job. So I have created a program and I want to submit here. Okay, good, cool. So how do I do that? I can do that by CLI, command line interface. So you go to job management and you see all the jobs here. So I have been running few jobs prior to this session for few things. So you can see this thing already listed here, but I will do it again for you. So let me. So you need to install Azure SDK command line interface, and when you install Azure SDK command line interface, install Azure CLI, install Azure CLI for Windows, you will be able to see this command line. You can see this command line and it will look like this. You can see in the title bar Windows Azure SDK command bar. Now when you have this, what all you need to do? You need to actually connect to the Azure, to which account you want to submit this job. So I have written the code here. This is a code that I want to run. Okay, and I want to run on cloud. Okay, so first of all, I need to actually log into that specific environment, right? So I will say as AZ login. That's the command. So when I say AZ login, it will ask me, it will open a browser and it will say which account you want to connect. So I have multiple accounts, but I will say, okay, I want to connect to this. Now, when you are connected to this, you have to set to a specific, see, you can see this. You have run this command and you have got all the details you are connected to it. Now I have a subscription ID. So what's my subscription ID? It's this ID. So I need to connect to this subscription. So what I will do is I will set this to this one. So I will say AZ account and I will say set this with this account ID. I don't need this one because it doesn't have a space. And then I can just press enter. The moment I said enter, E8, let me try in double quotes, it is fishing that. AZ, this is an example account list. Here. If we open this, Azure command prompt, AZ login. I select login space. Then I have here I get it. And I say is account set minus S. It's of case. Okay, the thread was run. Fine, fair. So I say account AZ account set minus S. What does it do? What it has done? It has connected me to this specific account, this specific thing. So let me show you. This account is connected. Fair enough. Now what I want to do, I can see all the workspace list that is there. So I can say AZ quantum quantum workspace list. Okay, so this gives me all the workspace list that is available there, and it will list all the quantum extension also if required. Now, how will this specific thing, as I told you, it can have multiple resource group, and each resource group may have quantum workspace. So I need to tell that which specific quantum workspace I am looking for. Okay, fair enough. So I need to give few details. What is its location and what's the workspace name, where I can submit the job and etc. Right. So let me give you one by one detail. So I can say, okay, that this is a workspace, and in this workspace you want to set something. What you want to set? You want to set few parameters. So the first one is that Azure Quantum is there. Azure Quantum, and that's what I have created. Then I want to set what is the workspace name. So what's my workspace name? QETCI-demo. This is my workspace name. Then what I'm going to select? Location, which is mentioned with the FLL, which is East US, right? And then I say or arrange in a tabular form. Fair enough. And I say this. Okay, table. Okay, my spelling mistakes. Table. Now it is setting it up. So now what it has done, it has connected to me to the actual account which I have created. Fair enough. Now I can submit my job. Okay, so where is my job? My job is in some specific place where this specific directory is there. So I will move to that directory. So let me go to that directory. So I will say std, and I will pass into that directory specifically. So that is there. C and users, EM Gupta, and I think it is in OneDrive. That is where I always keep. Okay. Okay. I put this in double quotes. Say OneDrive. Yeah, OneDrive Microsoft. Then I say QC. Quantum computing, that's the folder name I have. Then I say demo. Then I say, what's the folder name? Random number generator, right? Random generator, right? So then I say, okay. Now I need to submit the job. Okay, so now I'm doing submission. Quantum. So submit. And when you submit, you actually have a target. Now, when I say target, before that, I want to show you what are the targets. So target meaning where you want to submit. I told you there are multiple hardwares on which you can submit. So we can see that what are the list of hardware. So target, actually this is target list -o and table. So if you see here, you will see all the list of possible things. You see this? So I have QPU. So like you have CPU in classical computers, central processing unit, which is known, you have something called QPU. This is a real quantum machine. And there is, if you submit it, you have 5,346 second wait time. It's not that this kind of machine is not available, that you can just go and run. This is a costly machine and very hard, very inaccessible hardware. So even if for free, you have to wait this much of time. That's an average queue time. It may be less as well. But if you want to run on simulator, the way we have run on simulator. So remember when we have run it here, we have run .NET run -4. Now this, whatever you were doing here, this was running on simulator. Okay, but here what we are doing, we are running. No, it's not running. Okay, I'll start building it first. So when you have run it earlier, you have run it on local simulator. That's local machine. Wait, let me remove this. Control AC, file save, go to program, save. Okay, 1 second, guys. Start debugging. I think this should run now. Yes, it is running. Okay, here enough. Okay. What happened? I'm not asking for resource estimator at all. Okay, now it's running. Okay, so when I was running like this, I was running on a local simulator of my local CPU, just my laptop as of now, where these out of these 4 qubits, three are 1 and 1 is 0. But here what I can do, I can submit into Azure Quantum on quantum simulator or even IO and QPU. So let me show you how to submit on the simulator first. So I can say Azure Quantum job submit, and then I say target ID. When I say target ID, what is my target ID? I am trying to submit it to where? I'm trying to submit it to this target ID. So I'll take this and I'll submit it. Okay. And when I'm submitting it, I have to give a job name so that I can see. So let me give a job name, and I can give a job name called demo. Demo live is not bad name. It's not working from morning. Okay. I'll give example demo 1. Okay. Example demo 1. And then I will say table, so in a tabular format. So what all I have done, I have said submit this job, Azure Quantum job submit. This is my target ID. This is my job name. This is job name will be something like this, and table. Now there is some parameter also in the program. What is that parameter? That parameter is n is equal to 4. So let me try this if it works. So I have said example demo 1 is the one. Let me go to this. Let me go to job management. Let us see if example demo job 1 comes here. Let's put it here on the side. Yes, it has submitted. And you can see example demo job 1 is coming in the cloud. Now let's understand this window a bit. This window is having an ID. That's a job ID, where you have submitted an IONOQ, one of the hardware provider, to Microsoft as a partner with Microsoft. And what is targeting? It is targeting the simulator, not the actual hardware. I will submit where you will see this way also. And it is waiting. What does it waiting? It is waiting for the simulator to do some execution. What is submission time? This is submission time, and completion time is not there because it is still waiting. And it will tell you what is the execution time and cost estimate of this as well. Okay, so let's go there and see whether it is executed or not. So I want to see the status. So you can see the status either by refreshing here or by command window. So if you want to see from the command window, no problem. You can again run a command called Azure Quantum job. And now what you want to do? You want the output to be seen. So you will say output, right? And of which job, and then there is a job ID. So let me take this job ID with me. and I say this job ID minus O table, and that's it. So if this has run and successfully completed, it will tell you what is the the value of this. See, you can see this. This means that it has 2 power 4 possibilities, and each of them are equally divided in order to see the result of this. So this is the way you can see. So let me show you this way here also on the portal. Let me show you here on the portal as well. You click on, you refresh this, it will show succeeded in the state. You can see the succeeded now. You can see it took actually 1 second. It started on this time. Completion time was this. It has a lot of different gap, but that was waiting time as well. Cost estimate is 0. If you click this specific job here, you will see detailed window where it will tell what is the name of the job, what is the ID, who was the provider, state succeeded, cost. It is a simulator. It took 1 second. It was submitted this time. It was removed this time. Shorts is 500. So what is shorts? Shorts means how many times it has been run. This program has been run. So 500 is the default value here. Okay, complete हो गया. Okay. ये start कर देना थोड़ी देर. So then job, if you go to download job input, and you will see what was the input. And if you go to download job output, you will see the output. So let me show you the input and output. You go here and you say, okay, open this file of. Oh, it is my file. I'll show you 1 second. Where is download window? This is my download window. Download. Okay, machine is too slow to respond. 1 second, guys. Bear with me. Okay, so this is my window, and if I go there, I can open this here as well. You can see now. So either you can open the output in the cloud window, Azure cloud window itself, or you can open it in the command prompt where it looks like this. Got it? You can pass the 3 and you can see. Let me pass it with the 3 one. I say example demo 2. And I say n is equal to 3. So it will come. How many states will come? 2 power 3. That will be 8 states. So if I say this, I can see example demo 2 sometime in this window. Okay, come on, demo 2. This will come here. Yeah, it is example demo 2. With n is equal to 3. You can see the 2. It's in waiting time. It will execute. Perfect. Now, if you wanted to submit, let us say demo 3 onto the real QPU.
Amit, I have a question here. This frequency 0.0625, can you interpret that for us? Like, what would that mean? So every result is a frequency here, and all the frequencies seem to be same. So yeah, what would the interpretation be of the result?
That's a 50% chance. If you have 2 states and you are saying that it will be in superposition, if you have 2 states for the qubit, for a single qubit, what is the chance probability for 1 state?
Okay, so here you have like 0, 0, 0 from there to 1, 1, 1, 1. So let's say if I pick up anyone, let's say 1, 0, 0, 0, 1, and the frequency is 0.0625. So what would actually that translate to?
That means that this specific state has this much probability to occur when the measurement happens. It is equal probability because we have, it is telling you, you told me, right? When you run this 10,000 times, what is the probability of falling it into 0 or 1? Because you have 1 qubit. Here I have 4 qubits. So when 4 qubits you have and you collapse, what is the probability of a specific state is this much. That's the probability of that state.
Okay.
If you all add all of them, it should be 1.
Okay, so if I'm adding all of this, that was also my second question. If I add all these frequencies, it will come up to 1, is it?
Yes, ideally, yes.
Okay.
Okay. Okay, perfect. Now, if I say demo 3 and I want to run a real QPU, so you need to only change this parameter, which is this. Rather than simulator, you are running it on the QPU. That's it. And I say, okay, run it on QPU. Say enter. And you can come here and you can refresh it. Okay, 2 was run. I can show you the output of second one, but let me just complete this one. So when you submit this, I will see the output of this one. It is not yet submitted, so let it submit. So it was 3. So it will show you the frequency of, it was also 3. The demo job 2 was 3. So I will use this specific ID of this one, and I will show you the job output of this one, that how this job is submitted in the Azure Quantum. Okay, it came. So let me show you the output. This is different output. This one, I want this one because it has 3. Okay, do you see this? 2 power 3. Okay, perfect. So now if I refresh it, you will see that it is actually submitted to the real quantum, and you can see it waiting. The results will come in some time and you will see it later. But anyways, let's move forward with that. So this was this window, and somehow that S did not work. Okay, let me wait for some time and I'll come here.
Amit, I have a question regarding the shots. So earlier we see that there are 500 shots. So are we controlling these shots, and how actually it resembles to?
If you want to control the shot, there is a parameter called -s. You can reduce it to 1, 2, whatever you want to have. There is a option of controlling that as well. I can ping you the parameter of the PowerShell script, and in that you can control that shot as well.
Okay. Thank you.
Where is my window? Okay, so give me a second. I'm opening something. Okay. So where is my window? Yeah. Okay. Fine. So I have to. Okay. So we have done this. Let me try resource estimator again if it works. Otherwise, I'll tell you something else. It is resources estimator. Oh, it is resources estimator. 1 second. That's a spelling mistake. That's what I was thinking. Okay. Resources. Okay. So that was the one thing. Just okay, now it's coming. I think I had. So this should be covered now. This is only I have to. Okay, fair enough. So resources estimator is a place where it tells how many resources it will use. So you see C0 gate, qubit, qubit Clifford, R, measure, T, depth, width, qubit count, and borrowed width. These are all different types of matrices that are reported. So what does it mean? When you actually go to any quantum hardware and you writing program in Q#, you need to know how many gates will be used. So for example, if you see this, if you're running this, you need 4 gates, right? So you see that I need 4 clipboard. So clipboard is the run count of any single qubit clipboard or poly operations, poly X, poly Y, poly Z, or Hadamard gate or CNOT gate, and blah blah blah. Okay, CNOT is a count of CNOT gate. I'm not using any CNOT gate, that's why 0. Measurement is how many measurements I may have. If it is there, it is not, measurement is not being shown, that's fine. And similarly other things as well. Now I'm not going deeper into this, but I can ping you one resource link where you can find more about resource estimators. Okay, I will ping in the window. So you can see more about the resource estimators at the link that I have given in the chat window. And all these resource estimators that you are seeing is built on the top of a class called Quantum Trace Simulator. Okay, or based on that, it has been, created. Okay, fair enough. So now let me quickly move to little bit more deeper things which I wanted to cover. That is a quantum random number generator. So let me show you the quantum random number generator code. Let me check if I have written the module for you at least somewhere, so that it saves your time and my time. So I will use this operations like this, and this will require some more classes. It will require open Microsoft.quantum.math is required. And what is now? I think all should resolve automatically. I'll say operation. I'll make it a single qubit. This doesn't give problems. And use 1 qubit. One qubit, and I apply Hk to that qubit. And then when I apply hash to qubit, I return simple measurement. Okay, so what I'm doing, I'm measuring a simple qubit here. Simple qubit, M of Q. Write this problem. Type of P is not written. This is a Q, return M of Q, and this operation is done. Okay, then I'm taking an operation of this one. And I'm taking this result, and this is not my entry point. I'll make entry point somewhere else. So measures each bit, return, and I'm not returning an array, I'm returning a simple Q. So this resolves. Okay, cool. Let me explain you a bit quickly so that you can get it. So here you know what I was doing. I was actually creating a simple qubit, right? And I am collapsing it. Now here what I'm doing is I'm trying to say maximum is 15, and I want to generate a random number between 0 to max, which is 0 to 15, and between max is a parameter that I'm passing into function. Now this is one function, this is second function, and this is third function I have written. Okay, and in this is my entry point. So where what I'm saying is repeat, it's kind of loop. Mutable is a bit, and it stores lot of this one, and I'm saying IDX bit, any variable, where what I'm saying 1 to 1 dot bit I max. So when I'm saying bit size I max, I'm saying to this one keep adding the bits, because I know randomly any bit can be generated, and when randomly bits will be generated, you keep accumulating them into the output variable, and until output is less than equal to max. If yes, it is there, you return the output and you get the value. So let me build this program quickly. So this is a way by which I'm trying to actually generate some random number between this and this. In the meantime, I can show you the cloud also for the previous job if it succeeded. It is still waiting for the QPU because I told you 5,336 seconds. It told us it might wait. We might have to wait. This much is the wait time for the real QPU. So it is waiting still for getting access to the real quantum hardware. Now let's run to this. Now you can see it is coming here. Very good. Fine. Let me run this. And I will run this again. So now I have to run this. And is there a parameter? No, there's no parameter to this program at least. I said .NET run. I got 43. Again run. I got 32. Again run. So the more you run, you will get the a random number, a real random number. Now let me jump to my PPT where I left you, so that I can cover logically two topics. So I have shown you the library, how it works. There are different libraries: standard library, numerics library, custom library, and quantum machine library as well. Then we have seen how the simulation resource estimation work. Simulator, I have shown you how resource estimator work. Hyphen resource estimator is one parameter by which we can run this. And then we have seen some demos as well. One program of Hello World we have seen, and then.
Okay, Amit, I have one conceptual question on this QRNG that you showed.
Yes.
So, when you generate a QRNG number, let's say between 0 and the max, which is 50 you gave here, is that the only input that is required for a QRNG generation, or you also have to give some kind of values for any superposition or any entanglement or anything, or it's just that you give the maximum value like max and that's it? It automatically
only the max value, that too I have defined. If you want to pass as a parameter, you can pass as a parameter also. It's up to you. In this case, I have defined it as a constant variable here.
Yeah, so that's the only thing that is required, right, for the QRNG. Nothing else. You don't need to put any other input.
No, not now, because what I'm doing internally in the program, I'm generating the bits. That's random. I'm adding the bits and ensuring that it is less than max. If yes, just output it. So if I keep running this, it will give me the different random number. Sample will be random number 0 to 50. You can increase this limit and it can be increased as well. That's also possible. I can decrease it and I can build it and I can run it again. It will be that much of limit.
So there is nothing like seed here. No seed for the random number, right?
Okay. I'll come to it. I'll tell you. I'll explain you that part as well. In computers, which is classical computers, there is nothing called random number, to be honest. That's the that's the limited understanding sometimes we have. There is something called true random number and there is something called pseudo random number. Computers today, I'm not talking about quantum computer, be very clear. I'm not talking about quantum computer, I'm talking about computers. Classical computers today, when you write a program in any language, they are not true random numbers. They are never a true random number. They are actually a pseudo random number. So the pseudo random number generators don't generate true random numbers. They are mathematical construct that give you numbers that are actually a deterministic sequence. It's just that it's deterministic in a complicated way. For example, in a way that has some property similar to true randomness. You have a seed, and if you provide a seed, there is a code written in the compiler of any language, and it generates the deterministic value of you. But that code you don't understand behind, so you say it's a random number, but it's not actually a random number. That is called pseudo random number. So for a lot of applications, pseudo random numbers are perfectly fine. But for some of them, we want real random numbers. Now, how do we get the real random numbers? Real random numbers is something where you have something really which is unpredictable behavior of randomness. That comes through the electrons movement, that comes through the photon movements, that comes from the qubit movements. So since qubit is made from these elements, we are really not sure at any given point of time t, what will be the behavior of the qubit, because it is superposition. And because we are trying to measure that behavior at any given point of time, and we are seeing something, it is not deterministic, it is random. That's why the quantum will generate true random numbers. Are you understanding what I'm saying?
Yeah. So actually, I was mentally comparing with some typical random generators, the pseudo random generators, which like, will take inputs from the keys that you type, or, the temperature of your maybe the laptop.
That is nothing but your seed. You can provide a seed, it will generate a number, right? And you provide, see, until you put a, so okay, so what is true random means is that you cannot deterministically tell, not even by algorithm. So when you write a function, any mathematical function, forget about computers, if there is a parameter which is never deterministic, the result will always be of any complex or easy function, it will always be undeterministic. And quantum provides it because of the nature of the qubit. The nature of the qubit is vulnerable. It's never determined. It can never be told until it is in superposition. So that's why it generates a true random number. So when you say I'm providing something, you're actually giving a seed, right? And there is no concept of seed. So in quantum mechanics and in quantum computing, measurement is such a fundamentally random thing. It's a source of true randomness, because it's not some computation that brings us the measurement result. It's not some hidden variable that defined it. It's a proper physical randomness process. That's why when you see, when you read more about quantum hardware, you will understand someday that it is completely very difficult to actually capture the state of an electron or ion. That's why Microsoft is working on the topological qubit, where you have it, you actually can control the state of a qubit, which can help you in calculation. But controlling the state of a qubit itself is a very daunting challenge in real physics. It's easy to say, but it's really, really tough, because the temperature has to be extremely low in order to maintain the state of the qubit. And you try to maintain the state of the qubit, and the next moment, if the temperature is going or any factor is going, the qubit will be lost. So that's why topological qubit is being made in order to do that. Because if it is lost or it has a lot of noise, then for error correction, you need another big set of qubits, which is not possible. So that's why this provides you true random thing. Hope I was able to make some.
So one thing, let's say I write a simple Java program. Okay, I mean some complicated Java program, sure, where I use a random number generator, and then I have some business applications based on that random number generator, random number that was generated using a pseudo random number generator, right? So now let's say I don't want to change my business application anything, but I just want to leverage the QRNG that Azure is providing in my Java program. Yes. So can I just replace my random number generator, the pseudo random number generator call, with a call to your QRNG, and yet use my Java application and go ahead with the usual, the business.
Absolutely, you can do it. You can do it. What you have to do is this language, as I told you, if you remember, I have written one comment here. I'll show you. You see this line? Interoperability with classical.
Yeah.
Any output that you do, you can take that output and can feed as an input to other classical program as well. That's quite possible.
Okay, yeah, then that will be valuable, because
See,
I don't want to miss out on my actual classical application, but just want to leverage the QRNG that Azure is providing.
No,
So,
see, of course, the introduction of quantum doesn't mean that you are going to replace quantum in everything. There is a value to it. I mean, if you wanted to, go and write a plus B program, you will not need a very big hardware machine of quantum. You will just write a classical computer on a laptop. That's it. So depending on the needs and the complexity of the problem, we choose that which quantum do we need to quantum machine or not. Not for every problem we should use quantum computers. It may be overqualified for that as well, or not necessarily kind of thing. So yes, if you think that way, it is quite possible, mathematically and theoretically, and even practically it is possible. Okay. So right. Yeah, perfect. Any other question, or we can move ahead? I'm short on time. I need permission.
Yeah, go ahead.
Devika, is it okay if I borrow 10 more minutes from your time?
Sure. Okay. We would need to give a break as well.
Sure. Yeah, perfect. Okay, so true randomness is that specific thing, as I have shown you the program as well. And there are some links also that you can try on katas, quantum katas. So I will quickly introduce you to the katas as well. Let me show you that specific part. I'm grateful to actually Divya also, who gave 10 minutes from her time also to me. Okay, let me run it. So you have a couple of links. So quantum katas is a good way for anybody who is starting on the quantum computing to start on this. And in quantum katas, this is a way for self-learn. These are the packages that are for self-learning. So if you want to self-learn that how does it work, what are the different options, what are the different applications and all those things, you can actually use quantum katas to learn. And quantum katas give you a basic introduction of concepts as well. That all that detailing is always there to make you understand that what are the functions and all those things there. So let me quickly. So these are all different options that you will see in the quantum katas. Is there anywhere random number generator, or I can show you tutorials? Oh, binder is taking more time. Let me show you once another window. It is there. So once it opens, it will open like this. Here you will have lot of examples. For example, complex arithmetic, linear algebra, qubit, single qubit gates, and so on. And this is the example I have shown you. Okay, so if you come here, binder is not found because this is a different window, but I think it should be opening here soon. So you will see the window where the code will be something like this. It should be appearing like this. Yeah. So when you open this, you will get two random generators is this all detailing, and then you will see that what is superposition, how does it. You have seen this in Divya's single thing, and then you will have operations. So you can write your code. These are exercises. Generate as random number bit. Generate 0 or 1 with equal probability. Okay, can you find a better way to implement this operation? Right? Then you can actually write this and you can run this. The moment you run this in Jupyter Notebook, you will see an output. Then second exercise, generate a random bit 2-bit number. This is also I have shown you, right? Generate a number of arbitrary size. And then this is an example I have shown with the n bits to you in the Q# code and Visual Studio Code. So similarly, all these exercises you can try on your own in katas, and you can learn that how to learn the syntaxes, how to apply quantum operations into Python language through Jupyter onto katas. So this is a self-paced learning modules that you can always go ahead and try yourself. Let me see if it is binder is ready. Yes, binder is ready. So I can click this, and you can see here that it is showing you this way. And yes, it is ready. So suppose if you want to write this specific thing, and I have told you use qubit is equal to this. I say UK, use H, Q, this one, and I say okay, result -1. No, not -1. I say M of Q is equal to 0. And if this is, let's say, 0 or 1, and run this. This is a random bit, and you can see whether it is running or not successfully. If it is able to run successfully, it will come here. So binder is a online package that you can use. If you are not connected to internet, you can first download the QDK and the Q# extensions on it, and then you can run it in local machine also. I'm running online, so you can see it has passed successfully, right? And then you want to do this, then you can say okay, percentage. You want to run on simulator, simulate random bit, and when you say simulate random bit, it will show you 1. Okay, again simulate random bit 1, again simulate random bit 1, again simulate random bit 0. So see, this is the same code we have run in Q# in Visual Studio Code. This is the same code we have run in the Python also on the Microsoft Katas. So you can try all these things at your own pace whenever you want. I will ping you the links in the window. There's the chat window. So you can say, where's my PPT? Okay, there's the PPT, and I will try to ping you all these things. You can click any of them, wait, and try yourself at your own pace. So, okay, so katas are covered. Now quickly, 5 more minutes, or I think I will squeeze up one more concept and then I'll go over. So now the last part of the discussion is Dweis-Joshi algorithm. So I'll not go deeper into it. I will tell you the math problem statement and mathematical intuition around this, and then you will come to know that what I'm talking about. So the problem statement is Dweis-Joshi. Actually, you have seen the two random number versus pseudo random number. Here, this was the experiment that was done by Dweis-Joshi in around 1985 to show the quantum supremacy of over classical computing. Now you know a lot of things that Divya had talked about. Why classical quantum is better over classical? Not in all senses, but in the places where it is required really, and how fast it can grow and how fast it can execute and give you the results. So one of the problem statement was given by Dweis-Joshi to prove the quantum supremacy was this Dweis-Joshi algorithm. And here is the problem statement. The problem statement is, given a Boolean function, we have to find out whether the Boolean function is a constant or a balanced function, okay, and determine which type of function it is. Now, if you see this case, let's say if there is a function called f of this, and I'm passing 0 and I get always 0. If I pass 1 and I get always 0. Or if I pass 0, I always get 1. Or if I pass 1, I always get 1. This means it is a constant function. That's the definition of a constant function. In 1-bit case, I'm only talking about 1 bit now, as of now. But if I'm applying 0, I'm getting 0. But if I'm applying 1, I'm getting 1. That means it is a balanced identity. Whatever you pass, you get the same. Whatever you pass, you get the same. Or if the case is like this, if you pass 0, you get 1. If you pass 1, you get 0. It's a inverse identity, inverse balanced. So this is called inverse balanced, and this is called constant 0. But if you write the same program in a classical way, how do you write? You write, okay, f of 0 is 0 and f of 1 is 0. It's a constant. If f of 0 is 0, but f of 1 is not 0, which is 1, it is balanced, and so on. So if you see this very closely, how many control path you have seen? 1, 2, minimum 2. To come to print a statement, you have to compare minimum 2 conditions, not less than 2 conditions, right? If it is coming here, for example, if it is you are passing 1, then it will come here, and then it will come here. So minimum 2 conditions you need. Now, can we do with 1 condition? Can we solve it in the order of 1? So if you have seen the data structures, you know the order of complexity. The order of complexity of a program is either n log n, n square, n log n, or something like that, right? Here, the complexity is minimum 2 control paths to run for a program to run. But can we do it with quantum computing in just 1? Yeah. So that's possible with quantum. And how does it happen? In quantum, it happens with the gates, and every gate in the quantum is a unitary matrix. Okay. So if I see 1-bit gate, we need to apply the in the quantum, you have everything in the order of matrices, linear matrices. So if you see, this is an identity matrix. If you apply identity matrix into 1 0, which is a 0th qubit, and this is 1 qubit, you get 1 0. You see, you passed 1 0, you got 1 0. Let me put it this way. You passed 1 0, you got 1 0. Here you passed 0 1, you got 0 1. So this identity matrix, when you apply, you get that it is a balanced identity. Now, when we come to second one, I am passing some other gate, and I'm coming to know that, okay, if I apply this, it reverses off. That is called X gate. If you have seen X gate, or if you don't know, later you can learn it. This is X gate. Similarly, for the constant 0, if this is 0 and this is 1, 0, then the output for this is there, but we cannot find the input. Similarly, for constant 1. Now, if I see a box, let's say this is my box. This is my box that does calculate this. Then, if I'm so I cannot do it with 1 bit. So I need something called auxiliary bit, another bit in order to develop it, qubit. And then I say, okay, if it is getting the value there, then it is constant 0. If I put X gate, because if you see the last the previous slide, I'm applying the X gate here. This is nothing but your X gate. X gate in the linear form is 0 1 1 0. Okay, and then if you apply, it is a constant 1. If you apply C naught is another gate. If you apply C naught, there's a lens identity. If you apply balance inverse, you apply C naught plus X gate together. So if I put all these conditions into one box and I say, okay, I'm getting it to this way, I can say, okay, this is there. And the fourth condition is nothing but my Y XOR Fx. So you pass Y, and Y XOR Fx is something that you get in the right side. And this is the Deutsch circuit. So Deutsch circuit, I mean, it is too much for some of you to digest, but just to make you aware, this is my auxiliary bit, means extra bit. I still have one qubit only passing, and I'm applying H gate to it, which will put in superposition. I'll put this also in superposition. And these are the state before the applying the gate. This is after applying the gate. And I pass it to a circuit, and X becomes X, but Y becomes Y XOR Fx, and I have H. Now, if I see the bit of H and it is same, I can say whether it is a constant, or if it is not same, what it may be a balanced one. So if you see here, if 0 is passed here and 0 is coming here, I can say it's a constant. But if I am passing a 0 and I'm getting a 1, I can see it's balanced. And that was my problem statement. Within one qubit, can we make a circuit by which the detector can tell what is the type of qubit it is? That's a Deutsch algorithm. And if you pass this to multiple qubits as a generalized function, we say, okay, this is for multiple qubits, and I get that. And if the same condition is applied, then I can say, okay, this is Deutsch-Dosha algorithm for this one. And my condition was same, either it's a constant or a balanced function. So for multiple qubits, what happens is, if it is a constant, if it is 0, then it's a constant. If it is not a 0, otherwise it's a balanced function. So you can read more about Deutsch-Dosha algorithm, and I can pass you the hands-on links of also the same. But the idea is very simple. Within one operation, are we able to identify that whether a given function is a constant function or a balanced function is nothing but a Deutsch-Dosha algorithm. Okay, so I think I should stop here, and I can open this for Q&A. This annotations, so that you can see that. And you can see that real quantum computer is also succeeded, and it took almost 3 seconds. And you can see the output of that now. I can show you here actually. Copy job output. Okay. Yeah, you can see the probabilities of this in a real quantum machine as well. Okay, fine. So this is all I have to share with you. In fact, I can you can find the same thing about Deutsch-Dosha algorithm also to try if you want here. I can find out. Yeah, there is the Deutsch-Dosha algorithm. So if you want to try, this is here, random number generator is here, and you can try the other programs also over quantum katas. So with that, I'll stop. I'll hand it over back to Divya or Reena. And I'm really sorry for eating up your timings, other speakers' time. Yeah. Any questions? Am I audible?
Thank you, Amit. Thank you very much for that. So, yeah, we'll just have a 5 minutes break in the interest of time. And Devika, can we resume at 11:55? And Devika is going to cover a very important, interesting topic on how to use quantum optimizers, right? It is there are a lot of use cases that have found benefit today. So please come back for her session in 5 minutes, please. We can start off at 11:55. And thank you very much, Amit. And please continue to post your questions if you have anything, and we'll answer this.
Yeah. Thanks, Divya. I have pinned few resources as well in order in case somebody wants to have the visibility of that, and you can note all those links and you can read more about that there. I will try to see some more links if I have for QDK as well. So give me a second, I'll just try to see. So if you wanted to have the introduction to quantum algorithm, you can go here. I'll bring you the link. And if you wanted to run the algorithm, how to run and all, you can see the things here. And if you want the overview of quantum computing and everything, you can see the detail here. These are all links that I can share with you so that you can, go deeper into the quantum space and learn about it. Yes, sir. You have any questions? Please go on. While break is on, people can still post questions. I'm here available. I'm not taking any break so that I can help you clarify. Let me suggest how best this can be understood for a fresh student. So, okay. So, sir, is your question is how can somebody, how a fresher, what a fresher should understand or what a fresher should concentrate on in quantum computing? Is that your question?
Yes.
Okay. So, see, the idea of quantum is very straightforward. There are a lot of, if you see the theory of automata, there are a few problems which are NP complete and NP hard problems as well. I'm going a little deviating from the topic a bit, but yeah. So for many problems which are NP hard.
Amit.
Yeah.
I mean, what I meant by fresh is like a fresh student who joined into a technical program. So they may not be even aware of what is automata, computer architecture. They are fresh about to know about the binary systems and everything.
Okay.
They are at that.
So okay.
What I want to understand is that is it possible to reflect that particular quantum perspective at that particular beginning stage of understanding a computer onwards, and then can we divert it from that side or not?
Yes, you can always do that. But see, normally whenever somebody gets a new concept, they always wanted to get into application of it. Where do I apply this knowledge, right? In that case, if they are not aware of the limitations of the classical systems, it will be difficult for them to digest or appreciate the value of something new. If I do not know what are the problems with the landline phones, I will never appreciate the wireless connectivity with mobile phones or cell phones, right? So the idea is that if they have some knowledge about classical systems and then they jump into these things, it will make more sense for them to digest and appreciate the concept. So for fresh students, if he's really fresh, we can introduce them to the topic with some examples, which can tell them the results of the applications that can excite them about the possibilities. But if they want to go deeper, they need to have basic understanding of classical, and then they can jump into quantum. Directly coming into quantum is possible technically, but it's very difficult for them to appreciate the wonders of this area.
True.
Yeah, but yeah, to some level, we can introduce them. Yeah.
Yes. I think Amit, a session from that particular nature will be very helpful.
Sure, sir. Is it Chalam, sir?
I'm a reference from Chalam.
Okay, sure. No worries, sir.
Yeah.
Hello.
Yes, sir.
So is there any certification kind of thing available for from Microsoft? Like IBM is providing associate degree for Qskit, right? So is there any that sort of thing for QAsh?
I think a lot of content is available, and Devika, correct me if I'm wrong. I think there is some certification program in basic quantum understanding as well from Microsoft that is publicly available. Give me a second, I'm just trying to find.
So Amit, we do have many learn modules where you can apply and learn more stuff from, but there is no official certification as such. We would have one in near future, so please look out for the same.
Sure. So the Learn module that is publicly available, can you ping the link of this to the chat window? Can you find that link whenever you're free? So yeah, see, right, there is some links that you can use in order to learn. Let me also try to find. So, yes, I think the docs is there. This one is there, which is publicly available. I'm pinging you the link, guys. Oh yeah, she has already pinged. Thanks. Azure.com, yes. You can say azure.com/quantum/learn also is one of the resource where you can go and learn. Either you can go there or you can both of the resources. The one that Divya pinged and one I pinged. You can go to any of that. In fact, if you go there, you have the guided path for you to learn. There are different modules, and in each module there is there are some videos, there are some exercises, there is some knowledge check, there is some summary, and you can always go there and learn from there. Did I answer a question? Somebody asked about the resources.
Yeah. Thanks.
Okay, and any other question from anyone? And thank you for joining. I understand after 5 days of work on 6th day, if you have somebody pulling into the session and all like this, it's difficult. But yeah, thanks for joining and having a curiosity to learn all of you. Best of luck, guys. Yeah, over to you, Devika. Thanks.
Thank you so much, Amit. And yes, thank you, audience, for joining us. We'll quickly go to the optimization part, which is planned for the third session today. I know the break has been quite small for you, but bear with us. So I'll be covering the optimization piece, and especially from the point of view that I'll be going through a job shop scheduling problem. So we'll practically mathematically solve a problem, try running it and see how quantum optimization solutions can make the difference today. I'll also show you where it is making the difference already and what are the possible other avenues that you can contribute or maybe brainstorm on. Okay, so we'll firstly understand what an optimization solution is, because except we do that, we won't be able to harness the power or understand what this is bringing to front. We will go through the demo, that is the job shop scheduling problem. Before even we start coding, I will explain what the scenario is, what the problem is all about, what are the constraints. So every problem has certain constraints. We will define some notations because that is going to bring some understanding and will be basically helping you to code the solution as well. Next, we will basically form the problem. So now all the English-like statements that we have gathered in the scenario, constraint, and notations, we'll put it all in a problem formation, and those will be actually mathematical equations, which can either be executed through loops or other techniques that we would see. Finally, we'll code the solution and look at the result. We'll also see how to verify that. And towards the end, we'll see the industry application that Microsoft has targeted today. And of course, the next steps that you can take to be part of the community. Okay, I know you have seen the slide quite some time now. Just to emphasize, and this is a very important slide, from the point of view of quantum computing, Amit has done a wonderful job, and I think you are up to pace with it. What I'll today be covering is the optimization part of it. So basically, if you see, the optimization is happening today with the languages that we are aware of. Basically, you can code in Python or C++, and this is running on hardwares which are available today at scale. So these are CPUs, GPUs, or FPGAs. So these are available today, and we are harnessing the physical system power that is available classically today to provide this optimization. Now, we will be requiring at scale, the hardwares will be required at scale. So you can leverage cloud solutions like Azure is providing to help you in the journey of your optimization. Now, there are optimization solutions which are already available. through optimization API. So you don't need to know how the optimization is happening. All you need to know is to represent your problem exactly in the right format. And I'll show you for a very simple problem today, the job shop problem, so that you are aware how to actually formulate and bring about the real problems that you are facing, and maybe try to optimize them and see if there is more meaning to it than getting added. Moving ahead. Now, what is optimization? So we cannot move forward unless we understand what we are targeting here. So what is optimization? To be, say it at a very simplest form, optimization is basically a process of selecting the best possible solution amongst all possible solutions. So there, a problem can have multiple solutions, but what I want to select is the best one. Now, how do I define this best? Best can be anything. It can be a low-cost solution. It can be maybe a quickest time solution, or maybe and lowest environmentally impacting solution. So basically, you can define this best as anything to everything. It depends that what you start with. So basically, you have to define your problem well. And that is the case with any problem solving, right? Now, basically, to speed things up, usually people, what they call the optimization as is the cost factor. So the cost that is required in terms of time or in terms of running the solution, basically they want to minimize this cost. So does that mean that only minimization is the essence of optimization? No. Maybe you are running a program where you want to maximize the energy. Then what can you do? In the same techniques that we are applying, maybe you can basically multiply it with -1 and try to minimize it further. So that is essentially like maximizing something. So the problem formation is something which you have to tweak a bit to get the desired result. But essentially, the meaning of the optimization is only choosing the best solution where your best is defined very clearly to you. Okay. So this is a very plain graph that is showing you the configuration on the horizontal axis and the cost on the vertical axis. So what are configurations? So there in real life optimization problem, if you see, there will be a very complicated setup. You would have so many variables that are moving back and forth. There will be so many constraints that are applied, and each and every variable that will have permutation and combination of values to be taken up. So this is what we call as the configuration. So there can be hundreds and thousands of configuration subset. Now, with each configuration that you choose, some may be right, some may be wrong, or maybe some might be more optimized or more beneficial than the other. So basically, the cost on the vertical axis actually show you the cost of choosing a particular configuration on the horizontal axis. So this is particularly, okay. Yeah, so this is particularly the cost of choosing this configuration. So this is the graph which is representing our solution this way. Okay. Now, not all solutions are best. So there can, in often optimization problem, what happens is that we are stuck at local solutions. Yeah. So some local optimas, if you see, this is also a minimized solution according to the surfaces we see around it, but it's a local optima. This is a global optima. So what we are trying to achieve with this optimization solution is a method which not only provides us a better solution, but also avoids these local solutions, which might be giving us an illusion that they are better than the others, but might not be.
Devika, I have a question on this graph.
Yeah.
See, cost, I can understand the y-axis, like as you move up, the value of cost is increasing. But for the configuration, when you move in the x-axis from 0 towards the right, what do you mean by the increase of configuration? How do you translate that thing?
So basically, it's not, Yeah, it's not an increase of configuration. Yeah, pardon me for the graph, like it's always shown that way. It's not an increase. It's basically different set of configurations that we are trying to address. So I'm not saying that this one is in terms of value, it is greater than this one. No, what I'm trying to say is that all these points that you see are different set of configurations. So let's say you have hundreds of variable. This one would have different values for those 100. This one would have certain different values. And for all the values, we are looking at the cost. So what cost do I get? Maybe this cost is cost of building the product, or maybe the time required to build this product. So cost can be anything. But configuration, with configuration, I mean that with this set of configuration, I might not do that great, but I am doing better with this one and best with this one. So basically, that's the entire essence of this graph.
Okay.
Okay. So let's illustrate this graph. Let's add more meaning to this graph with traffic minimization problem. The aim here is to actually reduce the congestion on the road and thus increase the basically the comfort of the people. So what are the different configurations that you can think of? So from the x-axis point of view, the configuration will represent the different combination of the routes that I assign to a particular car in an automated fashion. So I am given the set of routes, I'm given the set of cars, and now I am mapping which car will take which route if starting from A and reaching to B. Now in that solution, the cost is actually, what is the cost? The definition of cost is basically the overall traffic being reduced, or the time taken by the average car speed is basically reduced. That is the aim or the cost I am defining here. Now, we are highlighting some of the examples on the screen with each and every local optima and the global optima thing. And you can see the not so great thing is actually more redder than the best solution. And more redder the entire traffic congestion looks like, it is not that great a solution. So if you look closely at this one, you see a lot of red lines are there. So that means my configuration, what my configuration has done, it has assigned the same route to many cars. So that is why there is a lot of traffic. So this might be a better solution than the solutions chosen otherwise, but this might not be the best solution. Now, if I go on to the next one, which is the best one, which I'm trying to refer, this looks much more cleaner and less redder, I can say. So that means the congestion is a bit lower and the cars are assigned more diverse set of routes. So maybe when my algorithm, which is running, is actually assigning better routes to each and every route that a particular car will take. And thus from source to the destination, I would have lesser congestion and the average time would actually reduce. So that's the entire intent of it. Okay. So any questions in understanding the basic idea of what optimization is?
Devika, so when you talk about optimization, this is like even relevant to the old classical problems also, right? I mean, where when the quantum technologies didn't come, that time also the same challenges was there. We had to reduce the cost, right?
Correct,
in terms of either resources or maybe better performance or those things. So when you are bringing in the quantum angle, are you saying that you are able to use the quantum technology to solve the old classical optimization challenges, which were earlier solved using classical technology, but now with quantum technology, you are able to solve the problem better? Is
okay,
that so the final crux of the whole optimization thing that you were talking about?
Okay, so there are two parts of it. One, that of course there were problems being solved earlier and those will still continue to be solved the way they were. But there is a quantum itself is not just a technique or just another processing unit. It's a mindset. So with the quantum mindset, understanding physics much better in a much better way and in a much different way, we can actually improve upon, first of all, the existing quantum optimization solution, as well as we can leverage quantum hardware as well. But for now, what we will be concentrating on is the techniques that we can use today at the classical hardware. So in both sense, even the optimization techniques that we will be looking at today will be an improvement on how we do it classically as of now, as well as how we can leverage it once the actual quantum computers are here. But we don't have to wait for it. There are things that we can do today, and we are doing it as well. So like there are different ways to tackle any problem. Like you can range from using typical classical methods like taboo search or stimulated annealing, which we'll use today, to actually quantum inspired network. So it's quantum inspired word, and that is the buzzword here. So it's not all about quantum. It's the inspiration that we take from what is happening in that quantum world. And these methods can be like Monte Carlo or stimulated quantum annealing, which are basically purely quantum optimization techniques that we use. Okay, so as I mentioned earlier, all we have to use, so basically all these quantum optimization problems or classical ones, you don't have to formulate your problem again and again for the same. So Azure Quantum provides you with the flexibility that you can formulate your problem once, and then you can build upon it and basically try different optimization techniques on different set of value set, and you can basically build the problem once and run it again and again and see which one is working. Because ideally, if you see, there is no silver bullet, that it's not one solution fitting for all. You have to see, you have to brainstorm and actually look at which optimization solution is working for your case. So for that technique, we don't want you to get stuck into formulating the problem again and again for all the different type of simulators we have, or basically the optimization solutions we have. So what we're trying to do is we generalize that process. You do that once and you apply it to different Azure Quantum optimization services that are provided today. Okay, with this basic information in mind, let's start with the job shop scheduling scenario. So the job shop scheduling scenario, first I'll go through into what the problem is and what exactly are we trying to achieve today. So it's, of course, it makes much more sense to visually see what is happening and let's like take a problem and solve it. But without knowing what the problem is, it will be hard for us to relate. So I might be a little fast because the time might be a little shorter for us. But if you do not understand it, please go and visit the Learn module that we have shared. And we have a job shop scheduling dedicated module in the same. So it is a very well curated content. So you can go through it in case you're getting stuck. You might use the recording and that might make things more clear. Okay. Now, what is this job shop scheduling problem? What is the scenario? So we have certain set of jobs and it's like a to-do list. So each has specific processing time. So in real life also, when you're doing certain tasks, you have certain time associated. Like if you go for a walk, you maybe walk for 15 minutes. If you maybe go for reading a book, you might end up reading for 30 minutes. So every job that you practically see might be attached with some processing time. So that will be the scenario as well. Now, you might need certain machines to perform certain operations as well. Like you need a book to read a book, right? So we consider machine as the facilitator here, whatever you're doing. Maybe you want to log into a website and browse through it, or maybe find certain websites. So maybe imagine you going back to the site of Qubit and you refer to this video. So basically in that situation, you are actually needing a laptop or a desktop to perform that operation. That is a machine that is attached. So each job can further be divided into certain set of operations. So one complete job might be part of certain operations. So these are the jobs that we would be taking today. So very plain, like looking jobs which are in day-to-day life being used by all of us. So let's say I want to pay my electricity bill or maybe my mobile bill. Then I need maybe a laptop to log into the site, pay my bill, and finally print the receipts. So on the bottom of the screen, you see the machines that can actually be used. Now, for booking a plan or basically planning a camping trip, you need to pick up a campsite or pay online and then you print a receipt. Now, each and every machine that you see will be leveraged and will be mapped to each and every operation. But there are 3 jobs and each job has certain number of operations attached. So this looks very familiar to us because this is a real life problem. So I hope you are able to relate and you are able to also comprehend on the simplicity of the problem, yet we understand a very plain concept leading to a bigger problem being solved. Okay. Now the constraints. So basically, there is never a problem which doesn't have a constraint. So of course, you want to make sure that the solution, how do you define a solution to be a good solution or a valid solution? You have to define certain constraints. So we'll define certain constraints in this scenario as well. So each operation in a job actually needs to take in a certain order. So the first constraint is the precedence constraint. So operations in a job, you cannot, if we actually remember what was written on the previous slide, you cannot print a receipt of your electricity bill unless you pay it. So that is a pure logic thing. So you cannot break this order, or you cannot book a camping site unless you have picked one. So there is a certain order that we need to perform the operation in. So there is a precedence constraint. If any operation occurs before the previous operation that needs to be performed, then it's a violation of this constraint. The next one, that is operation once constraint. So what does this operation means? This operation means that if we start the operation, we have to make sure that it's getting completed. And if once you have started this operation, you shouldn't start this operation yet again. That means if you have picked one campsite, you shouldn't be picking one another. So that's a constraint we are putting. Like, do each of the operations that we have delivered in the previous slide only once. And once you start doing it, please complete it before proceeding to the next one. So that's the constraint. That is our second constraint, that is operation once constraint. The next one is no overlap constraint. Now, what does that mean? That means a machine, if being dedicatedly working on doing one task, shouldn't be actually stopped to do another task. So let that machine actually complete one task at a time and then assign that machine to another task. So that means if I have printing of electricity bill or maybe printing of my campsite booking ticket, then I can't do that simultaneously unless I have 2 printers, which are considered 2 different machines. So since I have only one machine, let's stick to the fact that I will only print one receipt at a time. So this constraint, any solution that follow these 3 constraints, is what is known as a valid solution. So what's the definition of a valid solution? Any job shop scheduling solution that can actually go through each and every job, perform all operation within the least amount of time, and provide me precedent constraint, like abide by precedent constraint, operation once constraint, and no overlap constraint. So all these constraints needs to be followed and abided by to make sure that my solution is actually following all the required criteria, as well as giving me the most optimized solution. Now, of course, now what is the optimized solution? Like I said, optimization is choosing the best solution. So let's be very clear of what is the objective here. So defining the constraint, and before we basically actually start coding, we should know what the objective is. Otherwise, we might get misleaded and we might not reach to the point where we actually intended to. So of course, the valid solution that we have discussed is the one that do not violate any of the constraint. But our goal is here is not just to find the valid solution, right? Our goal is rather to actually find a schedule that can minimize the time taken. So that is also our objective. So objective is schedule operations, all the operations in a way that the time taken, so the total time taken to complete all of them, that is, we cannot leave any one of them. I can have an optimized solution saying that I was able to complete the entire thing in 1 minute, where I am just doing one operation. That's not valid. You have to actually complete all the operation, and that we have to do in the shortest time possible. So we have to abide by the constraint, find a valid solution, And this solution should actually be doing all the jobs in the shortest time possible. Okay. So on one slide, now you know the entire problem. So you know all the constraint and you know what is the objective. So if anybody has any doubts, they can call it out. Like if you have the problem in understanding any of the constraint, or you, if the objective is not quite clear, any problem in understanding the problem before we proceed. Okay, great. Okay, now we need to define certain notations. So we just don't want to go haywire and get stuck in the variable names, or maybe not understand some things later. So let's clearly define everything right at front. What do I call, like how do I refer to my job, how I refer to my operations, what does it mean to actually pick a job at a particular time, how do I represent that? So every notation we are trying to basically put forward here. Okay, so I will define all my job with zeroth indexing. So I have 3 jobs. I'll start with J0 all through J2. So these are my 3 jobs that I will be basically performing, and these are exactly the ones which you saw on the first slide. Now I am putting a notation on top of it so that it's clear when we are coding also that job 0 is actually paying the electricity bill and job 2 is basically booking the dentist appointment. Now each one of them had certain operations associated. So for simplicity of coding, we will basically define them from O0 to O9. There are 10 operations in total. So I am naming them in continuous section, and I will do the mapping of each job being mapped to which all operation. So my job 0 is actually from 0 to 2 operation. My job 1 is from 3 to 5. And my job 2 is from 6 to 9. So basically I have 3 jobs, each having certain set of operations. And now I have given them certain numbers. So instead of these plain English statements, now if somebody says paying a bill, then it is O of 1. If somebody says choosing a time for my dentist appointment, then it is O of 6. So I have basically changed all the English statements into certain notations, which will be very useful when I start coding my program. Okay, further down the line, now I will have a binary variable defined. So a binary variable here is defined with x of it. Now I is the index of the operation, and t is that particular time of instance. So if my operation O of I, so that is, let's say, paying my electricity bill is an operation. So my operation O of I, if it is starting at a given time t, then I will mark x of it as 1. Otherwise, I'll mark x of it as 0. So this is a basic notation which states that when is the particular operation getting started. So we have certain processing time. So it will end at t plus p of I. So P of I is my processing time. Of course, everything that any operation that you do would take certain time. So P of I is the processing time of actually this particular operation O of I. So if I start at time t, then I will finish at t plus P of I. So this is plain logic that we are applying, that if a particular operation O of I operation is starting at t time, then my x of it is actually equal to 1 in that case, and I will finish my operation at t plus P of I. If my second operation, that is the subsequent next operation, is O of I plus 1, that is starting at, let's say, time s, then that will finish at s plus P of I plus 1. So the processing time of that respective operation. So I hope the notations are quite simple to understand, and these will help us in representing all the constraint in mathematical form. So understand these very effectively. Now, at the end, we have something called as the capital T. So now small t is actually representing our simulation time, and it goes from 0 to the capital T in integer steps, of course. Now, t is the longest we are happy for the whole set of jobs to actually take in total. That is the maximum simulation time. So what is the maximum simulation time? Maximum simulation time in our case will be summation of all the numbers. So as if you are doing one operation one after the other. That is like the easiest thing that you would do, right? So that is, you don't optimize the solution. You just pick up all the jobs, all the operation one by one, keep applying the machines and start doing the operation. That time you will basically get the maximum simulation time. So our small t is actually lying within that time. Okay. Now, the precedence constraint. So basically, each and every constraint that you see, what model we are basically adopting for the optimization is, we will apply a penalty to our optimization solution. Basically, we add, if we are minimizing the cost, we will add a positive value to this optimization solution high enough to actually be able to make the optimizer, like basically the optimizer should not choose this particular instant because it's going for the most minimum value. So if I add deliberately a higher value, a higher positive value, that will make it hard to choose a solution which is wrong, or basically where the constraint is getting broken. So where all we will apply a penalty, let's look at it. So in the precedence constraint, I will add a penalty every time O of I plus 1, that is the operation that is supposed to happen after a particular operation, O of I, it's starting much before it has finished. So basically that is two operations which are supposed to sequentially occur. That is O of I should be followed by O of I plus 1. Then O of I plus 1 actually starts before the O of I finishes. So basically, this is the penalty condition. I will apply penalty only when this starts before O of I. Next condition. Now, this is operation 1's constraint. So basically, what was the constraint? It was that my operation should start only once and it should complete. So here I am making a small assumption. I'm saying if the operation starts, it will complete. That's an assumption that I am taking. And these are small assumptions that you would want to take to make your mathematical model a little simpler to program. So what I am doing here, I am applying a penalty when the operation does not start at all. Like for x of it, for a given I is never 1. That is, it never starts. That's when I have to apply a penalty, because what was my objective? My objective was that all the operations should get performed, not just any subset of it. And then if it has started once, it is starting again. So more than once, if it is starting, then also it is a violation of this constraint. So it has to be exactly equal to 1. Now, how mathematically we'll program this, we'll shortly see. The next one is no overlap constraint. So basically, one machine can do only one thing at a time. So basically, we assign a penalty if every time we basically see that a machine is being assigned 2 operations at the same time. So this is plain like logic that one machine, if it is busy printing one bill, cannot be used to print another bill. So yeah, this machine is not capable enough of doing that multitasking. If you want to print 2 bills, again, as I said, you have to bring 2 printers. That is 2 different set of machine, maybe of the same type, but these are considered different machines. So unless that is happening, you cannot basically print the bills on the same machine at the same time. Okay, so let's start formulating the problem. Now, first of all, we'll start with precedence constraint. The first things first, we have chosen job 1 for it. That is the camp, like booking your campsite. Say that that is an interesting thing to do. Everybody wants to go out and have a campsite. So basically, we have to pick the campsite and then pay the online bill. Now, of course, the precedence constraint says that I cannot pay the online bill before I even pick a campsite. So that is logical. So what I'm going to do here is that I will define all the variables. So O of I, which we saw in the previous slide, is actually O of 3 here. So O of 3 should be actually completed before O of 4 starts. Otherwise, you haven't picked a campsite, you cannot pay online. So now the processing time of O of 3, that is picking your campsite, is 2 minutes. So we will mark P3 as 2 minutes. O of 3 starts at time t. Let's say any given time small t we started, then we'll finish at t plus p3, that is t plus 2 time, that is 2 minutes. Now, when should your O of 4, that is paying online bill, start? It start at time s. Now, s should definitely be after this finishes. So any value that is greater than t plus p3, greater than equal to, is a valid solution. So if you see, these are all valid solutions. So s greater than equal to t plus p3. So in our first example, if I start at 0, that is, I first of all, the first task that I do is picking up the campsite. It takes me 2 minutes to do that. I can pay my online bill anywhere from here. Now I can pay it at 2 minutes, 3 minutes, 4 minutes. I can pay it in any order. If I am starting at 1 and I'm finishing at 3, I can only start at 3. I cannot start at 2 at this, because s will not be greater than t plus p3. So that is an understood like constraint here. Now, we were adopting a penalty model. That is, we have to penalize the solution when things do not go right. That is, so all the solutions that you see right now on the screen are valid solution. What are invalid? On the last basically column, which I've just displayed. So if whenever s is less than t plus p3, we actually add a penalty to it. So we add a positive penalty to the solution when any value of s is chosen for the O4 that is less than t plus p3. So fair enough. This should actually make sense to everyone what we are trying to address. So O4 cannot happen even before O3 starts or while O3 is happening. It should only begin when O3 ends. So that is why 0 and 1 are also not a valid ask here. Okay. So let's put it up in a more generalized form and let's add formulas to it. So basically what we are trying to do here is that we have first we will be summing over all operations. So basically that this formula that you see, all the operations we have to perform this. So any operation that is actually happening in this set or in any other job, we are applying this constraint there. So basically in a particular job, whatever operations are there, we are iterating over all of them. So that is one loop. The second loop, the second sum is actually happening from all the values that are that have s less than t plus p of I. So whenever s is less than t plus p of I, only those we have considering. Wherever it is greater or equal, we saw those are valid solutions and we don't need to add penalty to that. So the summation of the limits actually are defined quite clearly here, and I hope it makes meaning to each and everyone. Now, why we are doing a dot product of it? When these two are 1, only then penalty would get added. If you watch closely, these are 1 only when the operation I will actually start at time t. And this I plus 1 comma s means the next operation start at time s. So now when these both are 1, that is they start at a time where s is less than t plus pi, that is the time we basically multiply and these are both 1s, then the dot product will give us 1 and we add a penalty. If any one of them is 0, that means they are not scheduled at that time. So that is when they are not scheduled at a wrong time, we don't want to add a penalty. And that is why we are not using OR operation, we are using AND operation. So when both of them are basically there. Now, how do I convert this into my code? This is a basic loop format. So if you know any programming language, you would know that we have loops. And for that, I am firstly using all the operation in the job. So for all the jobs, I'm actually taking all operations in the job from the time t equals to 0 to t minus 1. That is my or basically the maximum simulation time that I can get. And I will iterate over only these 0 to t plus pi minus 1, all these, and these are 0th indexing. So you see all the minus 1s there. And then finally, we do this multiplication. We add a penalty when these this condition is true. That is s plus t plus s less than t plus pi. So this is how we define our problem for our precedence constraint. Please stop me if you think that I'm going too fast, or maybe you're not getting any mathematical notation. Okay, going forward with the next one. So we are done with one constraint. Let's proceed to the second one. That is operation one's constraint. So now in operation one constraint, if you remember, our x of I t is equals to 1 only when our job is starting at time t. So basically x of 3, that is picking up a campsite, is 1 at t equals to 1. That means at first minute, we are actually performing the operation of picking up the campsite. And that is why it is equal to 1. Now, if this is happening once, that is the summation of all these is 1. Basically, my operation is starting at 1. Then we are good. That is, it's a valid solution. But actually, if you see, if I start the operation twice, so if you remember the English statement that we use, when we are going to apply a penalty, we are going to apply a penalty when this starts more than once or it does not start at all. So the first condition, that when it is actually starting more than once, that means the summation of all the x3, t values will actually be greater than equal to 1. So it has to be exactly equal to 1. Or it is equals to 0. That is, the operation never started. So in both these situations, the penalty needs to be added. Now, how do I form this mathematically is what we'll see on the next slide. So let's explain this. Let's break this down and see how we came up with this. So the first summation, this summation, of course, we were adding all the values. So if you go back and see, we are finding like a summation of x. So this is a summation operation. So that is why same summation operation for all possible values of t, we are actually summing this x of I t. So for all i's, we are going to do that. So x of I t, we are doing the summation. Now, if this is exactly equal to 1, what will happen? This will be 1. 1 minus 1 is 0. You take a square of it. You do this operation for a particular I value. What will be the result? 0. So if it is a valid solution, we are not adding any penalty. Now let's check for the other case when it is 2. So if this comes out to be 2 or more, then it is a positive value and we square it, we add it. Now what is happening? We are adding a penalty. We add a positive value. Now let's try a situation when we do not start this at all. That is, my summation is actually 0. So 0 minus 1 will be minus 1. We square it, it is 1. Now, why do we square this value? There might be a question, why do we need to add this square? Well, if you add a negative value, just in the last case, 0 minus 1 minus 1, if you add a negative value to a solution which we are trying to minimize, instead of adding a penalty, you are actually adding a reward. So we have to always add a positive value so that it goes up. It is being like we are doing a penalty to it. We want to punish it. It should know, that system should actually know that this is not the right answer. Instead of that, if we do not square this, what would happen? It would say, oh, okay, adding a 0 is actually giving me a benefit. Then it is serving as a reward. So basically, that is why to add a positive value always, we have squared it. And of course, we'll be performing this operation for all possible operations. So that is why we are doing a summation of I. So I hope this equation of our operation one constraint is also clear. Now let's try to represent it. Let's try to see how we will represent this in our code. So how we saw loops in the precedent constraint, we'll see, we have to mathematically solve it and see. Now we'll take a short example. We'll again go back to the pick campsite problem. We will mark this as x3 and the time period for this one is the processing time of 0 to 2. So here the capital T is 2. So my small t can only take two values, that is 0 and 1. So let's try putting those values. Now, once you're doing a square, what does it mean? You basically have to put this statement twice. So instead of making things more difficult to read, what I'm doing is I will replace x3, 0 with x and x3, 1 with y. So let's call this very simple equation. And I am not changing anything. These values still remain the same. But what I'm trying to deliver here is a little simpler approach so that you don't get stuck with the notation. So x plus y minus 1 square. So how do I write this square value? This way. Now pairwise keep multiplying it, just how we multiply any equation. This is a mathematical statement. So what will I get? I will get basically three terms of degree 2, 2 terms of degree 1, and 1 term of degree 0. So these are all the possible values that you get. So mathematically, if you want to represent this, for each pair of value, you have to find this equation. And these are all penalties being assigned. How we will assign this penalty in QSHA programming, I'll let you know. There is a way we can particularly put this problem up. Okay, so moving to the last constraint. I know I might be going a little too fast, but in case you want me to slow down for a particular concept, please do let me know. The next one is no overlapping constraint. So no overlapping constraint says that machine can only do one thing at a time. So basically, if you see, if I take 2 pair of it, let's say picking a campsite and paying online bill require the same set of machine, then what will happen? If I assign it at the same time, this is actually a violation of my no overlap constraint. So essentially, in the example that you see, it is working fine. Okay, I start at 0 time, the third job and the third operation, and I start at 1 minute, my fourth operation. So in this case, the violation is not there. Now, if you actually take a dot product of each and at a given time instant, the dot product will always be equals to 0. That is, no 2 operations can occur at the same time if the machine is the same. So that is why you get this series of 0. So if you do a summation of all these, what you will get a 0, and that's the valid solution. So we know what a valid solution is. Now let's try to see what is an invalid solution. So in an invalid solution, you would have the operation starting at the same time. Now what will happen? The dot product of that particular time instant will become equal to 1. And the summation of these are all possible values will for all possible period of time will actually become more than 0. So it has to be exactly equals to 0. So if it is more than 0, then it is something we should apply penalty upon. So we have already seen the mathematical form. Let's just provide the real equation. So for each machine, what we are trying to do, we are trying to do that I, T, K, and S for all the operation I and K, basically for all possible pair, what we are trying to do, we are trying to do at time T and S, whatever time they are getting executed. If these are getting executed at the same time and we are basically the dot product is equal to 1 in that case for any given machine, then we add a penalty. So they have to be exactly 0. If they're not, then we are adding a penalty. So this is basically all the constraint formulation. Now we are just writing it up in the same slide. So if you see, we started with defining the constraint. What were the constraint? We defined certain notation. We know each and every variable, what it means. And we against each constraint, we have a particular mathematical equation. That's how we will define a problem. Now, so far we are going good. We have the constraint, but we have to basically define the objective now. So if you remember, we had an objective. So the objective here is that the function is actually this. So we basically multiply each and every one of them with certain weights, that is alpha, beta, gamma. Why are we doing this? They should have certain weightage to say in the entire program. And the last one, this is another constant for the completion sake we have added. So every time, we'll explain this while we are doing the coding part of it. This particular is basically added to see where we are going wrong. Basically, if there is there is a minimum amount of time that will be taken, a lower bound and an upper bound. Any time that we go from lower bound to upper bound, that period of time we basically add certain penalties, so that even in terms of time of quickest solution, the objective also added one more constraint, right? So it was hidden in the form, but it is also adding one constraint, that is it should be shortest time possible. So every time we go beyond that shortest time, we add a small penalty to that as well. And for that, we also have this weight attached to it. And we add all of them, finally giving this capital H solution. So this solution is actually what we have to minimize. So we are minimizing this. Now the problem is quite clear to us, and we are good to represent this in the code. So I have this particular slide deck, like this example already hosted. So I will try to paste this in the chat. So if you guys want, you can also try along with me. Okay, this is the website. I'll try to copy this and keep. Okay, I have downloaded the solution. You can log on to github.microsoft.qio samples. If you go on to this one, you will find all the samples, much more than job shop scheduling as well. What I have done here for today is I have set it up the entire thing in my local environment. So I'm using Jupyter notebooks for the same. So I'll pull it up here. Yeah. So this Jupyter notebook actually has all the things that we need today. And this is running locally. So you can actually run this over Binder as well. I am running this locally. The same problem that we discussed is actually mentioned here. So the objective is the same, the constraint is the same. In fact, the slide has the same kind of jobs and operations as well. So nothing changes. So there are certain blocks that we have to execute. I'll go through each one of them. Already I have explained most of the stuff. Wherever necessary, I'll try to pick those up. But if you run through this and you read through each of the step, you will actually be able to visualize how your problem is getting built. Okay, so there are certain Python libraries that need to be included, so that's okay. Okay, next is building your Azure Quantum setup. Of course, once you are ready with the problem formation, you would have to be running this on a Azure Quantum workspace. So Amit has already told you how to basically set up a workspace. I won't go and repeat the same. Rather, all I would say is that you can actually go to the workspace. Yeah, I'll bring that up. So this is my workspace. So in my workspace on the overview page, you will find all the information, your resource group, your subscription ID, your name of the workspace, and of course the location. So all these information are quite handy for you here. I'll go back here and I have to just fill in this. Once you run this, you will be asked or you will be prompted to actually sign in, either here or while you are running your program in the workspace, either ways. So basically you would be running this program in a workspace and you need to tell this program where your workspace is situated. Now, for the interest of time, I have already run this and you would see the result. But once you start running, you would take about, so other blocks would run quite fast, but it will only take you some time to run the optimization solution. Okay, now we are defining the problem, we are calling it out, same things that we saw, how the annotations are there, what constraints are there. And now we will understand how to actually represent a problem. So in Azure Quantum Optimization solution, you have to represent a problem in terms of the term object, that is this term object. Now, what is the term object? Now, your term object is nothing but this kind of an object. So a term object can be like a constant term. In that constant term, your C is the constant part of it, and indexes represent what all variables are there. So if it is a constant term, it won't have any indexes, so you can represent it this way. Or you have a floating value. Basically, it can be a floating value, a real like your integer value. All these values can be represented here. So constant term will only have this C section. Your linear terms will have only one term in the indexes and a constant attached to it. So let's say these 5x0. So x0 will be your index and 5 will be your, so you just have to provide the index to the problem. So 0 will be provided. And then 5. 5 is the constant term here attached to this. So 5 is passed here. Now there can be a situation where you have two terms, or it's a whether you have two terms x and y, or you have like x square y squared like terms. We saw that in our problem formations, right? So if you have that kind of an issue, then xi dot x2, how do you represent? There are two indexes, so you represent 1 and 2, or if it is a square of the same number, you represent 3, 3. So basically that's how you will represent this problem. Any constant value 2 or minus 3 is basically taken care by this. Now, does that stop here? No, you can actually expand it to higher orders as well, for cubic or for more fourth or fifth power of the variable as well. So that's how you form the problem. So now every time we do a precedence constraint or a operation once constraint, we are basically adding problem terms in this problem. So we'll define a variable called problem. We would add terms in them. So basically terms is what we are collecting. So when we say we have to add a penalty, we basically add a term. That is, this value is not accepted, or maybe internally it has the logic of penalizing the results when a certain term is achieved. Okay. So what we are trying to do here, we are getting all the required input. So we are getting job operation map. So what all jobs are mapped to what all operation? Of course, we need that, right? Then we have machine operations. So which all operations are actually performed on a particular machine. So let's say my laptop is used for login into a website, while my printer is used to print a receipt. Now each like each operation would have certain processing time as well. So that is given here. And then total capital T time. So with all these information, we set our variables up. We sort them in proper order, and we assert that we are going good. So this is some sanity check, and this is nothing but basic Python programming that you have. If you're not familiar with Python, maybe you can refer to any online site for the same. And these are very simple looping structures. If you are familiar with any other programming language also, you should be able to get it. Then next, we are going to assign the values here. So all the processing time. So the processing time of 0th operation was 2. First operation is 1. That way we define this. We define the job mapping. Then we assign the machine mapping. So okay, your 0th machine is doing the maximum job and your second machine is doing the minimum job. So you define that. And then finally you process configuration, the first method that we defined with all these variables. Now we are defining this heuristic operation. So we have defined all the constraints verbally. Now we will be mathematically designing them, and using code, we will be stimulating it. Same example that I showed is available here as well. So you can go through them. And this is the penalty formation that we have done. So how do I represent this using a code? So to do that, I have to add certain terms. So as I said, whenever I want to add a penalty, I have to add a term. So what will I do? A terms is basically an empty array here. When precedent constraint method is called, I will go through all the operation in the job operation mapping dictionary. I will go through all the operation and present there. In time t to 0 to capital T, what I will do, I will go through any s value that is ranging from 0 to t plus processing time. And we are, of course, adding this minimum of this. This is logical. So t plus processing time, exactly what we saw in the slides. And we are adding the term. Now, how do we add the term? We add the weight, whatever weight you have to apply. Weight is basically you want to add the penalty and the indexes. Now, what was the two terms? The two terms was operation of I, whatever operation I was getting performed, plus small t. So at small t time it is happening, or small s time it is happening. So if you remember mathematically, it was written this way only. So t and s. So basically I plus 1, t and s. So that is what I am writing here. I, t, I plus 1, s. So exactly what I did there is what I'm trying to achieve here. Just this term formation is there. So you don't have to bother about writing these terms again and again for different Azure Quantum optimization services. You write this and this will run for all of them. So I can just change the simulation, like basically which optimization I'm using, and I am good to go. So that is why we have a standard format maintained. Now, this might not be the most optimized way of doing it, but this is the most logical way of actually visualizing it. So I've kept it this way. Then we have the operation once constraint. So the operation one constraint, I have already explained there. You have the idea. This is our answer. And to simplify it, we took it as xy, we multiply. Now there's a small change. If you look at it, x square, what was x square? X can only take the value 0 and 1. So 0 square is 0. 1 square is 1. So that is why we can replace these x square and y square as x and y also to simplify the problem. And this is something which we do in real life as well, right? We simplify the problem as much as we can before we give it to any optimizer solution. So basically we are left with only one 2-degree term, that is 2 of xy. So 2 is the constant term and x and y are the indexes that we have to represent. Let's see how we do it. So in the operation one's constraint, again, we are looping through all the operations in the t time range, and I append for minus x and minus y term, I just need one term, right? So I am adding for each term for for t value. And what was the coefficient? -1. So I am adding weight into -1. Now for s, I am going through each of them, and what I am these are my x and y. My x and y, if you remember, were basically value of t and s only. We basically took it as a special case. So there were x of 3, 0 or x of 3, 1. What I did was I assumed this to be x and y, and that is why I have to come back to the whatever I was assumed to this fixed term. So this time there are two terms that I have to add. It's a binary, like it's a or degree 2. So that is why I'm adding this. Now weight is 2. So I am multiplying the weight by into 2. Now there is a constant term as well at the end, and that needs to be added once. So I am adding one constant term. Here the indexes are 0. So that is basically completing my operation one's constraint as well. Next is no overlap constraint. So no overlap constraint also we saw. We basically took for each machine x of I, t or dot product with x of k, s, and wherever it is not equal to 0, we have to assign a penalty. So what I'm doing here, I am again going through the loops for all the machine, basically all the operation in a machine for ith operation and kth operation. If my I and k are not equal, so for the same one, I am not applying this. I have to go through in the range t with the range capital T. I will add a penalty method here. So that is the that means if t equals to s, that is meaning two operations are scheduled to start at the same time on the same machine, then we are adding a penalty. So we're basically adding this term. When this operation overlap, that means it has one has started, but the second one start in between. That is, you're printing receipt one on printer, and suddenly another command comes where you have to start printing your electricity bill now. So basically, two operations not only shouldn't start at the same time, they shouldn't be running at the same time also. So we add the running time from this entire processing time, we add penalty for that as well. And if operations are in the same job, so we have to, if they are in the same job, not only shouldn't they be actually happening on the same machine, they should be also in the order, like the precedence still applies. So if anything is violating that precedence constraint here as well, we are going out of order, then also we are adding penalty. So this code is in conjunction with what we saw in the slides. Now, the last one, the little lured validity check or a constraint, which was there, is the minimizing of make space. What was make space? Make space is nothing but the minimum time that will be required for us to, or the total time required for us to actually perform this entire operation. Now, this is a little mathematical and I will not go into this, but all you need to understand is this is a formula which goes into finding that this is the time which is there, and a very small factor we actually apply to penalize the solution whenever our time is exceeding the required amount of time, that is we thought as the lower bound. So from lower bound to the upper bound, we apply this additional penalty so that the solution can be made or can be improved even further. Okay, you can go through this content to understand basically what this formula is all about. And we basically calculate the penalty for make space as well. So from the lower bound to the upper bound. Now, once we put it all together, we have all the constraints here. We are having the formula. Now we will process configuration. So once we are processing these configurations, if you see, we are adding all these inputs and we are bringing in the process, just the first method that we called. Now we are assigning the values of alpha, beta, gamma, and delta. So we are applying all these values together. We are calling the precedence, the operation once, and the no overlap constraint. We are getting the terms here. We are basically getting the terms for make space objective as well. And finally, we are adding all these terms together. Now these terms are what will form our problem. So next comes now actually solving this problem on Azure Quantum. So in the Azure Quantum, we have to actually get it from azure.quantum.optimization. What we are importing problem and problem type. So
Devika,
yeah.
sorry, before you go into this submit problem to Azure Quantum, till now, whatever you have said, this, I mean, till now, this, in these, like, it is basically, I mean, nothing about classical quantum, right, till now, because your problem statement, the 3 constraints that you made, you know, then the formulas that you mentioned, then the Python program that you mentioned, is there any quantum inspired thing till now, or right now you are going to enter into the quantum part?
So basically, I am using the algorithm that is running at the backend on Azure Quantum is what is quantum inspired. All you're doing is providing the right terms. How they find the solution is basically under that layer. So there can be different type of problem, like problem types and the solver. So which solver you use? There can be quantum inspired solvers that you use. Monte Carlo is one example, or you can use stimulated annealing, which is a pure classical method, which we used to use earlier as well. So these are all based upon which kind of solvers and the problem type that you are addressing. And you are free to do it. Like I just have to change the stimulated annealing to maybe Monte Carlo and I am good to go. I don't have to change anything on the top. Like my problem representation remains the same. How I am representing this problem is I have explained. How what is running and what is the Azure Quantum is doing basically are layered under the techniques which are provided. I'll show you the different techniques that are available. So these are the supported Azure Quantum optimization techniques. I'm using simulated annealing today, but you can go for quantum Monte Carlo as well. So these are some quantum inspired ones. How you do it is basically under the layer. You don't have to really care about it. All you have to care about is giving the right problem set.
So, okay, this quantum Monte Carlo or the other optimization techniques. So this basically is gives you the performance benefit, is it? Like, I mean,
Yes.
What does it do? And what is the benefit that you get? It's just the performance. That's about it, is it?
Yeah, performance as well as the more optimized solution. So the better the optimization technique, more chances are that you won't get stuck in local optimas and you will get a global optima solution. Basically, you get better solutions.
Okay.
Okay. Going back to this, so if I run, what will this actually return once I am basically loading the right modules, the problem type, the type of optimization technique, simulated annealing. And then I will basically define what kind of a problem it is, give the terms that I have gathered so far, and then pass this on to the simulator. The simulator will basically take 2 terms, that is workspace that I defined on the second cell, and the timeout. What is the maximum timeout? So if anything goes above 100 seconds, then it will time out. And then I run the job synchronously. You can run it asynchronously as well. The steps are given here. And finally, you get the, you basically print the configuration. Now, this is very difficult to read, and it might not be very appealing to any of us. Like, what is the meaning of it? How do I make sense out of this entire data? So we'll try to map this up into certain variables and see what it actually means. So this block of code, you can go through it and if you're interested, but basically it is mapping the results and showing us the result in the way which is humanly readable. So this is the configuration array. Now this is the problem we defined. So these are the job IDs. These are the operation IDs for each job. These are the operation runtime, that is the processing time. These are the assigned machines. So this was the problem. Now this is the operation matrix that says that x of 0i is 1 for 0th value. So basically this operation, 0th operation is happening at 0th time. So basically this operation is giving, this table is actually giving you the result you were looking for. So no operation happens at this time. And if you see, all the operations are happening, that there is never a situation where you don't see an operation not starting or an operation starting more than once. So, or there is a precedence violation. So basically it's a valid solution. We'll see how to actually see, there is a set of code which actually validates your solution as well, seeing that all the precedence, the operation once constraint and everything are followed. Now, this might again be like all theoretical. It still makes much more meaning than the configuration file which we saw here, but let's visualize it. Let's make it look more colorful. So this is the visualization. So machine 0 is what you see in the blue, and we saw machine 0 was extensively being used. Machine 0 was laptop in our case. Machine 1 was a printer which was used for more amount of time, but not as much as the first one. And the last one was your dental floss. So this was used only once. So you see the color coding here. Now the operation, if you hover over it, you will get the start time, the end time, which operation and which machine. Okay, so this starts each and every operation, which is basically under the same job, is following the precedence constraint. There is never a low overlap. So basically these pink values we don't have under the same time period. So if you see, all the constraints are being followed. So this visually gives you an appealing result that your solution looks valid. But still, to validate the solution, you can check for precedence, check for operation being once, and there is no overlap. And finally, you get a valid solution by all three. Like if all three are actually true, it's a valid solution. So I checked it and it's coming out to be a valid solution. Of course, the tuning of the alpha, beta, gamma, and delta, like in any optimization solution, is an ongoing job, and you can keep on optimizing and adjusting these. And you can use different solvers as well to come up with this problem and make sure you are doing good. So basically, all these will give us a valid solution, and this is the valid solution that you see. Any question before I move to the last part? I know I am 7 minutes over. I might take 2-3 minutes more.
Devika, so where we compare it with the classical solution and then say that this is better for quantum one.
Yeah, so you can actually, so as I was showing here, there are so many. So this is classical optimization approach. This is a quantum inspired optimization approach. You can run any one of the different kind of approach and see how your result is changing. So right now, in interest of time, I just could run one and show you, but you can actually mimic the same behavior. You don't have to, as I said, you don't have to go anything above this. So you just have to change the variables here. So instead of simulating annealing, you can call Monte Carlo or any other quantum inspired optimization technique. Find the results and actually compare and contrast how better it is. How is quantum better in terms of runtime or in performance?
Okay, got it.
Yeah. Moving to the last part is the case study. So how we are achieving the optimization today in different scenarios. So it's not like this is all in air and still not anywhere close to what we are trying to achieve. This is very well available today, and we are using, and we have provided like real world applications. So the first one is magnetic resonance imaging. All these information is in public domain, so you can go and check on this one if you want to know more about it. So magnetic resonance imaging is like a key diagnostic tool in the healthcare, and it has definitely played a pivotal role in the treatment of the most deadliest diseases. So it has been known to actually cure cancer or heart diseases or Alzheimer. And while there has been an immense progress made in this field, there are different set of improvements which can still happen. So the imaging quality, the time taken. So the time, especially the time taken that is there in this case, is quite huge. And there was a need to reduce it so that ranging from the old people to small children, they don't have to be seducted for that long, and they don't have to go through all the trauma of these exercises which are repeatedly provided or have to be improved. So their experience of getting into an MRI can actually be improved. Now, working with Mark, a professor from radiology and director of MRI research, Microsoft Quantum Solution has actually teamed up with the Case Western Reserve University to use bespoke quantum inspired solution, that is the quantum optimized solution, running on the classical hardwares to actually develop new pulse sequences for MRI scans. Now, what are the significant discoveries? Those are when basically optimizing for speed, the pulse sequences actually generated are typically shorter, resulting in an up to 3 times faster scan and delivery of comparable images quality. So you can actually see the quality of the images is not getting compromised while we are doing this optimization technique. Now, when optimizing for scan, the sequences can actually yield 30% improvement. We have seen that, and potentially leading to a better diagnostic and earlier treatments as well. Plus, these are much faster and thus are more cost effective and reduces the side effect as well. So these are some of the benefits that we saw in this MRI optimization with Case Western Reserve University. I might not have covered all the details. You can read online about it. The next one is reducing the traffic congestion. This problem we solved with Ford, and with this tie-up of Ford and Microsoft, which we together worked with, we have reduced the preliminary study has shown that we, in a setup of 5,000 vehicles, a 70% of decrease in consumption can actually be brought about. And this was only possible with quantum-inspired optimization techniques. Next is OTI. So we basically, OTI Luminous, we have developed a fast material design approach, and this is tailored to OLEDs and other electronic material. They work with the largest electronic companies in the world to actually design new material that are required for mass production and should be ready for that, enabling actually the next generation of consumer electronics. So OTI Luminous has developed software tools which actually simulate and predict the properties of new material, which can actually allow a larger pool of candidates to be screened than would be actually experimentally synthesized. So we helped OTI Luminous in their journey, and with their algorithms that are actually running on Azure Quantum, OTI Luminous is actually able to demonstrate meaningful results on problems of a commercially relevant size, not a small size, but a commercially relevant size. And this is only possible with Azure Quantum's optimization tools that are currently available and which we saw shortly before. Moving next is the further industry application. I want to leave you all with that so that you can actually think about what can further be done with an optimization solution. So like the job shop problem that we solve is not something which is hypothetical. I might not need job shop otherwise, but when it comes to real world application, imagine each and every task that we do. If we are building a car, each and every job that you do might comprise of smaller operations. It's a real life problem. You have to minimize the cost, like the time taken, and with the time minimized, you would want to actually deliver better cars as well as more number of cars. So that's one real life application of job shop scheduling. Similar to that, industry-wide application is there for optimization across automobiles, the government industry. Basically, you can do city planning, you can do healthcare improvement. We saw one example. You can do finance improvement, portfolio optimizations, or you can actually do a lot of things in the manufacturing engineering. One we saw job shop scheduling, others like chip designing, or maybe shop floor optimization. So there are different things which are already happening today or are being worked upon. And of course, I will leave you to much more ideas, and you can come up with more ideas and maybe try upon Azure Quantum with the free credits and see if you can actually achieve a more optimized solution for any of the application. So with that, I'll leave you to this slide. Already Divya has showed you this, and I think you should have all the handy links. But in case you have missed, please be mindful of noting these down and utilizing them well.
I hope these slides will be shared with us.
I'm not sure about that, but we can definitely come back on this.
Okay. At least the recording, I think, will be shared. Even
Yeah.
it will be good to share the slides also.
Recording is definitely getting shared. About the slides, we can come back.
Okay. Another thing, Devika. So now you see, you mentioned this different optimization techniques like Monte Carlo and also some classical optimization techniques also. So
Yeah.
let's say for the same problem, let's say the road congestion or whatever, if you are using any, let's say Monte Carlo, then for Monte Carlo, you will need a quantum computer or a simulator at least, right? I mean, you cannot use this kind of optimization techniques on a classical computer, right? Will you need a simulator or at least or a hardware?
Okay, so all of them is happening today. We are not involving any quantum computer. So a quantum inspired optimization is actually mimicking the quantum annealing method. So here we are running everything on classical hardware right now.
Okay, so just with being quantum inspired and still using classical computer, can you give me an idea like quantitatively how much performance benefit you get over a classical optimization technique?
Well,
Let's
that
say,
would
is it
be
like,
based
is it
on
same like
problem.
just okay based on the problem? Let's say for the road
Yeah.
congestion, for example. So if
Yeah,
the road
so
congestion is a problem, is it like the order of the scale is like exponential, or it's just a like 2 times or 3 times, something like that?
okay, so for road congestion with Ford problem, which we have solved, I already told it is a 70% of improvement that we saw in a like a Bing map setup with 5,000 vehicle problem. So for 5,000 vehicles, we saw 70% of improvement. You can extrapolate this problem, or maybe you can have better parameters, or maybe you can tweak them a bit to actually get better results, or at least 70% is what is basically observable right now. So you get good results with it, but of course you can't like have the same silver bullet being applied to all. You would have to do a lot of back and forth conversations as well as hit and trials to see which one is working for you.
Okay, so now you are saying that I mean you are going to, I mean this you are getting 70% benefit by using a classical computer. So let's say the same quantum Monte Carlo you are using for this, you are using a quantum computer right now, a real quantum computer. Okay. Yes. So does a quantum computer give a far more performance benefit over using quantum Monte Carlo on a classical computer?
Well, I can't really comment over that we have to see, run and see how much improvement it can bring, but definitely the potential that quantum computers show, it will definitely have better results than classical in certain situations. So it's not apple to apple comparison when it comes to classical hardware and quantum hardware, because it's a different palindrome altogether. So it's like a comparison, like building better candles does not build a better bulb. So it's that kind of a comparison. So you cannot do an apple to apple comparison here, but yes, a quantum hardware would definitely give a better performance, but not in all set of problems. Some might be actually the kind of problems which can be solved with classical hardware better. So for that, let's not always use quantum, is what my understanding is.
Okay.
So that brings us to the end of the session. We have taken a little more time than we planned. If there are any questions relating to my section or the ones Divya and Amit covered, please feel free to drop in chat or maybe speak up to us.
Thank you, Devika, and thank you very much, team, for your time. And we have posted the links that you can use to explore explore Azure Quantum further. And hope you all gain from this session. Thank you very much. Reena, are you there? I think the recording will be published on Qubit. Please follow Qubit website as well. So thank you very much, team.
Yeah, thanks, everybody. At least the Microsoft team and Reena for hosting it. It was a great presentation.
Yeah, thank you.
Hi, Divya and Reena, we are dropping off. Thank you.
Thank you, Amit.
Yeah, thanks, Amit. Thanks, Divya. Thanks, everyone, for joining in. And the recording, this was recorded, so this will be put up on the website, and an email will go out to all people who participated as to the recording being up. But otherwise, if you are impatient, you can keep checking the QETCI events page.
Thank you, Reena.
All right, bye.
Thank you so much, everyone.
Bye.
Thanks, everyone.